Okay. Okay, as I promised yesterday, we're going to switch to heterogeneous multi-core. You covered a lot on multi-core cache management. There was a portion on predictable performance in the presence of caches that are in the backup slides of yesterday's lecture, so if you're interested, you can go through those. And if you have time later, maybe we can get back to it, but I'm not going to cover that today. So this is what we covered yesterday. We looked at shared cache management, a bunch of different techniques, hardware-based, software-based, and shared private caching, trying to bridge the gap between the two and get the best of both worlds. And we talked about several techniques to make caching much more effective because it's a much bigger bottleneck in multi-cores. And we talked about how caching changes in the presence of many threads. So we talked about things like dynamic insertion policy, more probabilistic insertion into the cache, evicted address filters, trying to predict the reuse behavior of different blocks, and cache compression, making better utilization of the available data space, data store space in the cache. And there are a bunch of other techniques that we don't cover here, but this is just to give you examples of how to make caching more effective. And again, if you pull back a little bit, a lot of these techniques are applicable to other parts of the system also. Caches are used everywhere in any system that you build, in a distributed system, for example. And a lot of the caches are compressed, for example. A lot of the storage systems that we have today are compressed. In SSDs, for example, SSD controllers apply compression algorithms to get the best of the data storage that you have to have the maximum capacity. Okay. Today, we're going to switch to something else, although heterogeneity is everywhere, as we've seen yesterday also. But today, we're going to look at heterogeneity in the context of the cores or computational units. And then we're going to look at how we can exploit that heterogeneity to accelerate something that's hard, which is the serial parts of a multi-threaded program. How can we make things faster by taking advantage of heterogeneity? And these are some of the papers that we're going to look over. Okay, so let's start with a little bit philosophy, if you will. It's not exactly philosophy, but it's really a design principle in the end. So this is one of the key design principles of today. Why is this interesting? So heterogeneity is actually the same thing as asymmetry, and it enables specialization. Well, I already said that. You can contrast this with homogeneity and symmetry. And it's a general system design concept, and it's a life concept as well. Actually, when I gave this talk gave a version of this lecture to a much broader audience, usually it's the biologists that say, oh, these are principles from biology that we've been trying to understand, and it's good that real systems are applying heterogeneity into the principles. So basically, the idea is simple. Instead of having multiple instances of a resource to be the same, or homogeneous, or symmetric, design some instances to be different, or heterogeneous, or asymmetric. And different instances now can be optimized to be more efficient in executing different types of things. Things may be workloads, things may be different parts of a program, things may be different users, or satisfying different requirements or goals, like energy, performance, reliability. So you can actually design these resources to be heterogeneous for both of these. And as a result, heterogeneity really enables specialization and customization to the requirements that you have at hand for different workloads, users, and metrics, goals. So why do we want this? There are two real major reasons. One, in a system like computer architecture, there are different workloads that are executing in a system, and they can have different behavior. And when I say workload, it could be different applications, different users, but also different parts of a given application as well. Even within a single application, there is significant heterogeneity in the behavior of the application. For example, sometimes you may be scanning through memory, and then once you find the stuff that you were looking for, maybe you're doing a lot of operations that are relatively random access within a small memory region, right? Databases operate this way, for example. Database actually, today especially, there are multiple different types of threads that are operating on databases. Some of them may be scanning and looking for some data, and some of them may be updating the database, performing transactions. And these are really very, very wildly different behaviors. One is really streaming, scanning, and the other one is really, it needs atomic operations to update a very specific piece of shared data structure. So having the same type of core for both of them, or same type of memory hierarchy for both of them, actually may not make sense. Okay, different applications can have different behavior. If the execution phase of an application can have different behavior, the same application executing at different times can have different behavior due to the changes in the input set. If you give it a sorted array, a quick sort program gives you a different behavior than if you give it a completely random array, right? Unsorted array. And dynamic events also, what kind of user events are happening at that point in time. And as a result, this influences the locality, predictability of branches, ILP, data dependencies, as we will see serial fraction of a parallel program and bottlenecks in parallel portion of a program today, and interference characteristics also. Okay, and the second reason for asymmetry is systems are designed to satisfy many different metrics at the same time. Actually, today, there's almost never a single goal in design. You're really trying to juggle between multiple different goals to achieve a design point that makes sense for your product, let's say. So these are some of the design goals, right? Performance, efficiency, energy, fairness, predictability, reliability, availability, cost. And usually, you want to satisfy some of these metrics to some degree. And clearly, we've seen earlier, I'll give you examples of what we've seen in asymmetry, like the capacity latency trade-off in memory that we've seen, right? And our one of the solutions was a heterogeneous design, and I'll remind you of that. Okay, the problem with symmetric designs, it's really one-size-fits-all. It doesn't enable customization. It tries to fit a single-size design to all workloads and all metrics. So as a result, it's very difficult to come up with a single design that satisfies all workloads, even for a single metric, right? And also that satisfies all design metrics at the same time. And this holds true for different system components or resources. Everything we've covered so far and things we have not covered as well. Like when you're designing servers, if everything is homogeneous, you have very little room to optimize energy efficiency, right? But if you have heterogeneity knobs, even dynamic voltage and frequency scaling, for example, something like that enables you to make things heterogeneous. Like some server can be high voltage, high frequency, some server can be low voltage, low frequency. And now you can actually optimize your energy efficiency. If you need that high power server, you put it up into high voltage and high frequency setting. But if you actually have a lot of parallelism, maybe you put all of the servers or many of the servers or the servers that are executing the parallel part of the program to a low voltage, low frequency setting, right? So that's an example of heterogeneity, actually. You have a knob that you can tune to make things more customized to what's running. Okay. And also algorithms and policies as well, right? Algorithms can be heterogeneous also, like we've seen with scheduling algorithms in the past. Okay, so this is my pictorial view of what asymmetry or symmetry is. This is actually a really old picture. I think I drew this in 2009 or so. And one of the main reasons, just to give you a background, people didn't really buy asymmetry was a good thing for a long time. Actually, there's still people who argue homogeneity is good. And homogeneity is good for some things. For example, the programmer can now reason much more easily. They don't need to think about different things, right? So there was this workshop that National Science Foundation in the United States organized asking computer architects, what is the vision for the future? And this was one of the slides that I had for that vision. Basically, my vision was asymmetry everywhere. And there are some backup slides later over there. But basically, if you have symmetric, you have one size fits all. As a result, your energy and performance is suboptimal for different workload behaviors. But if you have something like this, at least, and this is just a pictorial view, it's an abstract view. It's not clear how you actually achieve this. We may talk about that. This enables customization and adaptation because processing requirements vary across workloads. And if you need more processing, you have this large core, let's say. But this is really a resource, not necessarily a core. Maybe it's a large cache, right? Or maybe it's something else. It's just an abstraction. It's more powerful over here. Now you can actually have a choice. You can execute the code on the best fit resources with minimal energy and while getting adequate performance. Now, how do you create this is another question, right? Do you have static creation of this? Or maybe you combine these symmetric things to operate like a bigger asymmetric thing, right? These 4 cores, if they can be combined to be a big core, wouldn't that be nice? It turns out people have looked at this is not an easy problem, and people have looked at it from both sides. Do you design a small core, 4 small cores, and add some glue logic to fuse them? This is called core fusion. That's one of the works that was presented a long time ago in ISCA 2007. It turns out that's a bit hard to do, especially if you want to get a really high-performance core, because if you want to get a high-performance core, you really want to minimize the communication latencies between different structures in a core. So it may be better to start with a really beefy core design, very large out-of-order execution windows, for example, very large pipelines, deep pipelines, ... and then try to turn off portions of it to get the behavior of smaller cores. So that's the opposite approach. Do you start with a very simple core design and do you try to fuse them? Or do you start with a really complicated core design and do you try to break it apart when you don't need many parts of it? And we're not going to talk about that in detail. That requires even more time. But keep in mind that these things don't need to be statically designed. Okay, so we've already seen examples of heterogeneity before. I'm going to cover this relatively quickly. So even the Cray-1 design, actually heterogeneity is an old concept which people have bought into. Maybe the multi-core has changed things a little bit. But Cray-1 design, a supercomputer, had scalar plus vector pipelines. I'm going to go back to that, actually. It was a vector processor, but it had the fastest scalar pipeline of its time, because they figured out that there are some code portions where you do need this scalar processing bandwidth. Modern processors have scalar instructions and SIMD extensions. Intel AVX is an example, right? We haven't seen this, but if you took digital circuits, we covered decoupled access execute. You basically, instead of having a single processor that does both access and execute, you decouple them. One is specialized for doing memory access, the other is specialized for execution. And then you feed data between them, and you have FIFO queues through which they communicate. That's a specialization within the core. We've seen memory scheduling algorithms. I'm going to show you more of this, just to make you recall. That's a heterogeneous scheduling algorithm. Heterogeneous refresh rates in DRAM, for example. Heterogeneous latency DRAM. Hybrid memory systems. Everything we've seen is actually heterogeneous, right? Well, everything really interesting, maybe. And heterogeneous cache replacement policies. We talked about this even yesterday, right? We kept saying that there's no single policy that performs very well for workloads. There are some workloads that are really LRU friendly, and you'd like to figure them out and apply the LRU policy to them. That's one example. Okay, this is Cray-1. Remember the GPU lecture? We talked about this. Essentially, I'm not going to go through this in detail, but this is the beefy part of the machine. But Cray recognized that you have the serial bottleneck in programs. It's not always parallelized. Not all programs are fully vectorizable. So if you don't do well in that serial part of the program, then you have a problem. So Cray-1 is actually the fastest machine of its time in terms of scalar performance. Not only vector performance, but also the scalar unit performance. So clearly, there's a lot of heterogeneity in here. We've seen this, hybrid memory systems, that's heterogeneity to get the best of multiple worlds. You want to put different types of technologies together and manage them somehow. So there's always a management overhead that comes with heterogeneity. We will talk about advantages and disadvantages. But you've also seen that, right? Throughput versus fairness, trying to optimize for different metrics. You cannot get the best of both worlds with a single policy, as we've discussed in an earlier lecture. So throughput-based policy is good for throughput, but fairness-based policies is good for some other threads. So we decoupled the policy to be heterogeneous, right? To get throughput, we wanted to prioritize the memory non-intensive threads, because doing so doesn't affect fairness as much. But for fairness, you actually have a different policy to ensure that these big threads or the elephants don't kill each other, right? Whereas prioritizing these mice and elephants is a good analogy for heterogeneity, I think, right? You're executing both mice and elephants in a program or in a system. Okay, this is not news, hopefully, right? You guys remember this? At least the slides. Hopefully the policies also. Okay, good. Okay, so this was the basic idea. We grouped threads into 2 clusters because threads had different behavior, memory-intensive and memory-non-intensive in this particular case. But you could actually make this even more heterogeneous, right? And the non-intensive cluster had a different policy. It was prioritized. And within the cluster, the less intensive threads were prioritized over others such that you could get the highest throughput possible. And within the intensive cluster, we shuffled the priority between the threads, or ranking between the threads, such that none of the threads became the top elephant for a long time. Okay, this is another example. And this is an example where we architected heterogeneity, right? We didn't need to do that, but we really made the policy heterogeneous. But the world is also heterogeneous, if you think about it. There are multiple reasons for doing this. One is workloads are heterogeneous, so you need to architect things to be heterogeneous. And the second is the world, the underlying technology is very heterogeneous, and we observe this in the refresh rate. It just happens because of manufacturing process variation that some cells have very weak retention times, low retention times, but many other cells have very high retention times. And if you apply a homogeneous policy for all of them, the same refresh rate, that's the worst case, you're clearly not optimizing for energy or performance. But if you actually distinguish between them and have a heterogeneous refresh rate policy, then you're clearly optimizing for both, actually. Of course, this comes at a cost, as we've discussed. So heterogeneity always comes at a cost, but enables your customization. Now you're customizing for different behaviors, different behavior of different cells. So keep in mind, some of the heterogeneity comes naturally, actually. This is true for voltage and frequency in different parts of a chip as well. You cannot have, because of, again, process variation, you cannot operate all parts of a chip with the same voltage and same frequency. You can, of course, but you need to operate them at the worst case voltage and worst case frequency at which you can do. But there are some parts of a chip you can operate at a much higher voltage and much higher frequency reliably, and there are some parts of a chip that you cannot operate at that voltage. So why not exploit this inherent heterogeneity in process variation and just make some cores low voltage, low frequency, and some cores high voltage and high frequency. Right? Now you have a natural heterogeneous substrate that you can exploit. This is another example of that. Okay, we've seen another way of architecting heterogeneity, right? This is one of my favorite examples because pictorially, it really gives the idea of heterogeneity very well. So you could have this, there's this clear trade-off between area and latency in memory. I'll call memory, but this is the case of DRAM. But any memory has this trade-off. You can have long bit lines, and this gives you higher capacity. If you want to make this faster, you can chop up the long bit lines to have short bit lines, but you need to add more sense amplifiers for that to get the same capacity, storage capacity. Now the problem is this became much more expensive. Your area has increased, right, as you can see. Because remember, the sense amplifier size, this is not to scale. The size of a sense amplifier was about 100 times the size of a single cell. So it's actually much larger than what you see over here. So if you want to make it smaller, you got to go this way. So there's a clear trade-off between area and latency. So how did we approximate the best of both worlds? We saw that there's a green here and there's a red here, and there's the opposite green here and the opposite red here. So a heterogeneous substrate tries to get the best of both worlds. Maybe not perfectly, but you start with this, you get small area because you don't replicate the sense amplifiers many times. But you create a region that's low latency by adding some cost isolation transistors over here and controlling them intelligently. And that's the idea of heterogeneous latency DRAM. It's called tiered latency, but essentially it's heterogeneous within a subarray, right? You get small area using long bit lines, and there's a portion that's low latency, and there's a portion that's actually high latency and high power. Now we can optimize, right? Before, we didn't have an optimization choice. Now we can decide what to put over here, what to put over here. We can decide when to enable this, when to not enable this. We could even go further, right? We can make some subarrays like this, some subarrays big, some big meaning long bit line, some subarrays short bit line. So you could actually add levels and levels of heterogeneity. But as you keep doing that, of course, your complexity also increases. So there's a clear trade-off between heterogeneity and complexity. Okay, one more thing. Even though we didn't cover interconnects at some point, we would like to. But in communication substrates, you have heterogeneity also. This is one example over here. For example, one processor, the Tilera multi-core processor. This is massively homogeneous multi-core processor. Very simple cores, actually. We cannot get simpler than this, maybe. But basically, even though the core substrate was very homogeneous, their interconnect was relatively heterogeneous. Basically, they had 4 packet switch networks and 1 circuit switch networks on the interconnect. This is basically, you have a router on each core and the cache slice, like we've seen yesterday. And then you can communicate with the next nodes in a mesh. This is tiled as a mesh. So you can communicate with 4 of your neighbors, except for the edges of the chip. Depending on the type of communication you have 5 different networks that are customized for that communication. For example, this one carries cache request packets. This one carries response packets only, because these are actually different. Because requests are actually much smaller, response packets are much larger. If you're getting a huge cache block, for example, here this may be 1 byte, this may be 64 bytes, right? You don't want them to be interfering with each other. That was one of the reasons why they decoupled the networks. I/O packets, they're going to somewhere else, usually the memory controller, because you do memory mapped I/O, so they're also different in characteristics. And core-to-core messaging, if you want to send a message to a core, maybe those need to be low latency. And there's also another network that's circuit switched, meaning that you don't dynamically switch at every router, but you set up a path first, and you record that path in every router, and whenever you send the request to the destination and you want to use that circuit, it's really fast, because the router knows exactly where to send the data. It doesn't need to make a dynamic decision, right? And you reserve that path such that now you get a predictable performance guarantee. And this is really good if you're streaming data through from one core to another core, for example, from one core to a memory controller. If you're sending 1 megabyte of data, you set up a circuit and then you push through the data and you get predictable performance, hopefully, because you set up the circuit. Okay, so this is another example. Even though the cores are homogeneous, the network is very heterogeneous, as you can see here. And that's a design choice they made. Okay, from life also, heterogeneity is abundant in life, both in nature and human-made components. We're all heterogeneous, I think. Cells are heterogeneous, organs, cars, buildings, ... I know these rooms are heterogeneous really well, based on experience in this class. Right? You guys know that also, right? Okay, so there's nothing surprising here. So why not make things heterogeneous also in system design? And then, as I said, some of it has to be heterogeneous anyway, because you cannot control that some part of heterogeneity. If you try to control it, you become worst case. You're really optimizing for the worst case. Okay, so another way of looking at this is really general purpose versus special purpose. Asymmetry is a way of enabling specialization. It really bridges the gap between general purpose, purely general purpose, and purely special purpose. If you have a purely general purpose processor, you have a single design for every workload or metric, and you want to optimize that design for hopefully average performance across all of those. Whereas if you have a purely special purpose design, you have a single design dedicated for a workload or metric, right? Like application-specific integrated circuits, ASICs, are examples of this. They can only do that task, signal processing, let's say. Even signal processing is very broad, but maybe a particular filter in signal processing, right? But asymmetric is somewhere in between. You have multiple sub-designs optimized for sets of workloads or metrics and glued together, like accelerators we have today, right? And the goal of a good asymmetric design is to get the best of both general purpose and special purpose. So let's look at advantages and disadvantages of this. I think I've given you a bunch of advantages and disadvantages, but we didn't really talk about them like in a single slide. So clearly, we can enable optimization of multiple metrics with an asymmetric design over a symmetric design. You can enable better adaptation to workload behavior. Of course, I'm assuming that you can predict the workload behavior and decide where to put stuff. You can provide special purpose benefits with general purpose usability and flexibility, hopefully. Right? You're not customizing the thing for a single application. You have really a bunch of choices. So hopefully you can get some of the benefits of customization while still keeping the usability and flexibility of general purpose. Of course, this comes at a disadvantage. You get higher overhead and more complexity in design and verification. You need to have higher overhead in management. For example, you need to figure out how to schedule onto asymmetric cores, as we're going to discuss a lot today. You need to figure out what to put in that different heterogeneous parts of DRAM. You need to figure out which threads actually go into different scheduling policies, different clusters, right? And we said that that's actually a hard decision. And you need to, one other disadvantage is you have overhead in switching between multiple components. This depends on your design, of course, but for example, if you're switching from a large core to a small core, it takes time. And that can lead to degradation. Yes? Is that a typo? This one? This one. So this is asymmetry. This is the advantages over symmetric design. This is correct. But this is disadvantage, right? So compared to symmetric design, you get higher overhead. Oh, okay. Yeah. Yeah, asymmetry always gets you higher overhead because you have more things to consider, naturally. Okay. Okay. So yet another example. And we've also seen this, right? Modern processors integrate general purpose cores and GPUs today. CPU, GPU systems. This is heterogeneity in execution models also, right? You have different execution models for a CPU versus a GPU. And there will be more. There's FPGAs, for example. So this is going to increase, I think. And the one key question is how do you keep things, how do you ensure these disadvantages don't dominate, right? Okay. Okay, so let's actually go into some more detail. This we've talked about. I'm not going to talk about that. But there are a bunch of problems that we've been talking about in class. And asymmetric designs actually can help those problems, like memory system, energy efficiency, and performance efficiency, which affect your scalability, and predictability and robustness. We can look at this. And these are some three big problems that are facing us into the future. But we're going to focus today's lecture on more of this, basically. Look at the multi-core or computation aspects. If you can we somehow scale the performance? We're going to talk a lot about performance, actually, less about energy, and make the system more scalable. And this may enable new applications and maybe better user experience. Okay, so we'll talk about cores. And there are some commercial asymmetric designs that already exist, actually, which is good. It's integrated CPU, GPU systems, CPUs plus hardware accelerators. Your cell phone is perhaps one of the most asymmetric designs that you have. ARM has big little processors. What I'm going to talk about predates some of that, actually. But this is actually used for energy efficiency, for example. If you're not energy efficient on executing on a big core, why not migrate the program to a small core? And then maybe you don't lose performance, but you improve energy efficiency. That's how it's used in ARM today. And as we've discussed yesterday, this is actually one of the first, perhaps the first asymmetric multi-core design, the first I know of. You have one core, control core, and 8 synergistic processing units that are like vector engines, actually. But we also discussed the downside of this. They don't have coherence in this case. Okay. Okay, and we have increasing asymmetry in modern systems. You can keep adding asymmetry to any part of the system, and there will be a use for it. And we already discussed all of this, I think. Okay, so let's talk about the multi-core design. Any questions before we jump into multi-core? This is all interesting, makes sense. Okay, good. Let's talk about the multi-core and from an asymmetric perspective. So if you look at these multi-cores, except for this IBM Cell broadband engine, as they called it, everything was heterogeneous. And this is also an old slide, actually. I like keeping these old slides. But basically, people designed these cores to be very, very homogeneous. And maybe it made sense. It was easy to do it, certainly. IBM was actually a little bit bolder, maybe, when they designed one of the first multi-cores. That was not their first multi-core, actually. Their first multi-core is not here, Power 4. Which we're going to talk about also. Their first multi-core was actually homogeneous. Okay, but what we want, we had this slide, part of the slide before. We want really n times the performance with n times the cores when we parallelize an application on n cores, right? And you can actually, this n cores can be n threads also, but I'm going to use I'm going to assume that we have 1 thread per core for now. Right? This is perfect scalability. This is called linear scaling, right? If you look at the number of cores, speed up, it's linear. Ideally, that's what you want. But what we get is, hopefully what you know, Amdahl's law, right? When did you guys cover Amdahl's law for the first time? Do they teach it in high school these days? No? Okay, good. Well, maybe this is what should be taught in a computer science education in high school, right? It's so fundamental, right? But which class? Do you guys remember? Parallel programming. Okay. Okay, second. Okay, that's good. Second semester, yeah. Yeah, Amdahl's law, I mean, you guys know this obviously, but we're going to look at that. But it's not, Amdahl's law actually deals with serial versus parallel. And it assumes that the parallel part is perfectly parallel, right? But that's not true also. You get bottlenecks in the parallel portion as well. So let's go back to Amdahl's law. Basically, this is what the speed up you get with n processors is. And also assumes that n processors are homogeneous. Right? Basically, you have this parallelizable fraction of a program. You cannot speed up with, you can speed up with processors, and you can perfectly speed it up. So this is the performance that you get with the baseline, and the parallelizable portion gets divided by n, because it's perfectly parallelizable. But the non-parallelizable portion, serial portion, you cannot speed up. As a result, you're bottlenecked by this portion. Right? So if your parallelizable portion is 0.5, the maximum speed up you get over here is 2, as n goes to infinity. Right? Okay, and this is a beautiful paper. Maybe we should assign that for reading, but it's only 3 pages. And Amdahl wrote this when he analyzed the applications, interesting applications, data-intensive applications of their time, of this time, basically. He found out that, most of them have F that's around 0.6, like 60% or so. And he said, well, we need good single processors to actually speed that up. So we're bottlenecked by this. And basically, maximum speed up is limited by the serial portion. So we have the serial bottleneck. So clearly, the processors you design for this portion and for this portion probably should not be the same. And that's one of the ideas that we'll look at very quickly. But if you look at over here, this parallel portion is also not perfectly parallel. This is an assumption. You get divided by n. But in real world, the real world is not that nice. There are actually 3 very fundamental reasons why this is not the case. Anybody know what those are? Shared what? That's right, yeah, that's one of them. I'll put it in a different way. What else? Okay, I'll put it in a different way, but that's good. You got 2 out of 3, even though the names are not perfect. One more. That may be hard, because the other 2 we've actually seen examples of this in this class. But the third one I've discussed also. Well, this is assuming that all of the processors have the same work, right? Same load. But that may not be true. So the first one is sharing, like synchronization overhead. You get a lot of synchronization overhead here if you don't do it well. Updates to shared data. The second one is load imbalance, the last thing I said. You have imperfect parallelization. Some processor may have a lot of work, some processor may have little work for various reasons. Programmer didn't divide the program nicely, maybe. Even though they may have divided it nicely, somehow the data sets are different and you get different behavior, right? That's also possible. My favorite example is you have a program that's divided. You need to count the number of different words in a page or different characters in a book. And you divide the book into number of pages. So you have, let's say, 32 threads, and the book is 320 pages. Each thread gets 10 pages. And one thread gets those 10 pages where there are pictures, so there's nothing to count. As a result, you have load imbalance because of the data input, right? That's a perfect example, and that happens in many kinds of data, right? So as a result, you're not perfectly parallel. Okay, and the last one is, as you mentioned, resource contention, right? Resource sharing overhead. This doesn't take into account, but we've seen that contention actually can destroy the performance of one thread while prioritizing another one unfairly. As a result, you don't get this perfect divided by n over here. And these are 3 fundamental things that people try to optimize whenever they write parallel programs and whenever they design parallel systems. And this is the difficult part, basically. How do you actually make sure you have a really good parallel system, multiprocessor, let's say, that minimizes these without making the programmer go crazy? So there's also that trade-off. You can perhaps get rid of all of this, but you can punt the problem to the programmer. Like the load imbalance goes away if you ask the programmer, make sure nothing is load imbalanced, right? That's not going to work. Okay, and you can eliminate the resource sharing with a lot of cost. You can replicate all of the resources. Not a good idea, as we've seen. And synchronization overheads, again, you can ask the programmer, don't synchronize, but then what do you have, right? Okay, so this is perhaps one of the most fundamental slides that we've had in the course. Don't forget these. If you come up with another one of these fundamental ones, let me know. That cannot go into any of these, of course, right? Okay, so we're going to tackle this one very quickly with heterogeneous processors, but we're going to spend a lot of time talking about at least these two, because resource sharing we talked about in different ways. Okay, so the problem that we're going to tackle is serialized code sections. There are many parallel programs that cannot be parallelized completely. Amdahl observed that. People keep observing that today also. Now, GPUs have been very successful in parallelizing actually many programs. So they've actually moved the needle a little bit. But once you parallelize it significantly, if your parallel fraction is, let's say, 99%, your maximum speed up is still limited to 100, right? Now you're at that point, you move the bar, sure, but what if you need more performance? You're back to square one, optimizing for that serial bottleneck. And they're caused of serialized code sections when it's sequential portions where only one thread exists, critical sections, barriers, and limiter stages in pipeline programs. Remember, we talked about this when we talked about parallel application memory scheduling. We're going to go into this a little bit more. And so critical sections are obviously sections where you have updates of shared data. Only one thread can be in the critical section. You lock, unlock, and only one thread can be updating that shared data. Barriers is a point where all threads need to reach before any thread can make progress. In my example of where we have 10 threads counting, where we have 32 threads counting, each counting 10 pages, the thread that gets all picture pages, finishes quickly because it figures out quickly that there's nothing to count over there. And all of the other threads count, and then they reach the barrier late. So this thread waits and ensures that its core doesn't make progress, right? So there's a barrier for you. Because once all of the threads count, you need to accumulate all of the counts into a histogram, for example. How many A's do I have? How many B's do I have? How many C's do I have? Or how many of these words do I have in this book? Limiter stages in pipeline programs, we've also discussed this, right? You parallelize a loop by turning it into smaller stages. Each stage may have its locality, and these stages communicate, but you can actually put the into different cores. If you remember the parallel application memory scheduling, you'll remember this. But we'll get back to this later on in this lecture. So these are all causes for serialization. For example, one thread may be reaching the barrier late. As a result, it's serialized everyone else. One thread may be in the critical section, and all of the other threads may be waiting for that thread. One thread may be the slowest stage in a pipeline program, so all of the threads are sending inputs to it, but this thread is not generating any output because it's the slowest, so it's limiting the throughput of the program, right? If you have producer-consumer parallelism, that's like that. If one consumer is not consuming fast enough because it's slow, then it doesn't matter how fast your producer is, right? Okay, so these serialized code sections are actually bad in many dimensions. They reduce performance, they waste energy, and they limit scalability. So one other optimization that, for example, people have proposed, if you actually have one thread that's reaching a barrier late, why don't you reduce the voltage and frequency of all of the other cores such that threads actually reach the barrier around the same time, right? That's an energy-saving optimization if you actually add that sort of heterogeneity into your system. But it doesn't improve your performance, right? That saves energy. Okay, we have this thread that's reaching the barrier for whatever reason late. I'm going to optimize the system to be energy efficient without optimizing that thread. That's a possibility. That may be a reasonable optimization, right? If your performance is adequate, you ensure that your energy is minimal given that bottleneck thread. Okay, there's also a limitation of scalability. Basically, this limits how many, basically, as you add threads into an application, your performance starts going down at some point because of these bottlenecks. So that's scalability. the maximum number of threads that you have that maximizes performance. Ideally, you want linear speed up, linear scalability, but you don't get that. And we'll see that. So actually, I'll show you right now. This is one example from one database, MySQL. And this is something that some threads do. You open some database tables, and you do some operation. Basically, you need to get access to the columns that you're operating on, for example, if you're doing a column scan as a thread. So to be able to do that, you need to open the table that really has locks for the database and the columns and rows. Once you have that, you can do very parallel operations. But to be able to get access to those columns, you need to access this cache that's really shared by many threads. And this is a critical section. Now, you can optimize this critical section to be minimal. But it turns out you get limitations because of this critical section. So this is the number of cores that you have, number of threads in MySQL with some workload. And your speed up saturates at 6. So at about 14 threads, I think, over here, your speed up is around 6. And then it starts going down because threads start contending for this critical section. They're waiting, and they're ping-ponging the data and locks between their caches. And there are also the other stuff that are in those 3 things that we've discussed, right? Maybe there's resource contention overhead also. So asymmetric designs, I'll show you an example where we could actually move this over here. So make the scalability better, and maybe there are some other techniques that can make it better, right? Okay. So what do we want in these? Basically, we have different demands in different code sections, right? In a serialized code section, maybe we want one powerful large core. In a parallel code section, maybe we want many wimpy small cores, right? If you can parallelize it perfectly. And this is a really good way of thinking about it. And these two conflict with each other clearly. If you have single powerful core, you cannot have many cores. And a small core is much more energy and area efficient than a larger core. Right? Now, this may not be true. People are looking into how to partition a very powerful large core into smaller cores. There's this idea called morph core that was presented in Micro in 2012. You may want to take a look at it if you're interested. I'm not going to go a lot into core design. But there is a huge area of research in this also. Okay, so let's be a little bit more concrete. What are these large and small cores? Small core is kind of obvious, right? It's in order, narrow fetch, maybe simple branch predictor, maybe no branch predictor. Actually, we'll see a small core that has no branch predictor. It has fine-grained multi-threading. Few functional units. You can think of this as like a GPU almost, right? A GPU has really, really small cores, if you will. A large core is, in contrast, out-of-order execution, very wide fetch, deeper pipeline, aggressive fetch engine, trace cache, for example, and many, many different types of speculation, some of which we've covered, some of which we're not going to cover. Basically, all of these techniques to extract single-thread parallelism, very deep out-of-order execution windows, for example. So, of course, clearly there's a design point. There's a continuum between these, right? But we're going to assume just these 2 for now, because as you keep adding different varieties, then you will actually have more of a complexity problem. And we're also talking about general purpose right now, right? You could actually have really accelerators that are specialized for different portions. But I'm going to limit ourselves to the general purpose cores for now. And large cores are actually power inefficient. For example, you get 2x the performance for 4x the area. That's one rule of thumb. This is a paper that I actually showed you earlier in the first part of this lecture. But this was written by folks at Intel, where they talked about the efficiency of large versus small cores. And as you can see, there are some metrics over here. Now, they don't tell you exactly how they got these numbers, but this is a nice chart to put over here. For example, there's this large core that's very beefy. Its normalized performance is 5 to 8 times that of the small core. Of course, this is very workload dependent, right? There are cases where if you run a workload and the performance of the large core is actually worse because it has a deeper pipeline. It has big speculation. So you need to be very careful when you do these comparisons. It's very workload dependent. But assume that for some workloads you get this, but the power consumption is much, much larger, 20 to 50x. And normalized energy per instruction is 4 to 6x, if you think about it. So if you have time later, we'll talk about a technique that optimizes for energy per instruction. But not right now, I think. Okay, so let's start a little bit historically also. Basically, when multi-cores were first designed, people were thinking about two directions. You can have large cores like this and tile them, or you can have small cores like this and tile them. And this was the first example of a large core that's tiled together. It's a symmetric multi-core chip, IBM Power 4. It has two powerful cores. And if you want to learn about it, this is one of the beautiful papers that IBM used to write on their core designs. It's an IBM Journal of Research and Development in 2002. Unfortunately, you don't see these papers that much from companies these days. But it explains a lot of things in the system itself. I'm not going to clearly go into detail other than saying that this is taking a large core of its time and replicating it. Two cores, out-of-order execution, large instruction windows, very wide instruction fetch. As you can see, large branch predictors, aggressive cache hierarchy, ... And IBM actually made the Power 5 multi-threaded. As you can see over here, it can run multiple threads. At the same time, it's a simultaneously multi-threaded processor. And for different threads, it has different return stacks, for example, different program counters. This is the exact opposite, the small part. Again, around the same time, a little bit later, Sun was designing the multi-cores also. And they were designing it for these workloads like web servers, where there's a lot of parallelism, and maybe there's not a lot of need for strong, very short latencies. Now, they actually figured out that they do need the beefy cores later on, but this was their design point at that time. Whereas IBM was designing more for workloads that are transactional, so where you really need the beefy cores, actually. So this is what Niagara looks like. Basically, you have these 8 different cores over here. Each one of them is 4-way multi-threaded, and they're connected to a very beefy memory system. So memory system was important. Memory system is important regardless of how you design the cores over here. That's why we started with the memory system. So I'm not going to talk about the memory system parts of it. But if you look at the cores, we've actually seen this when we talked about fine-grained multi-threading. Right? That was a slightly different picture, but essentially this. It's a fine-grained multi-threaded machine, 6 stages, dual issue in order. Very simple cores. 6-stage pipeline is very short, actually. It's 4-way fine-grained multi-threaded, so you don't need any dependency checking. You don't need any branch prediction, because branches are resolved at the end of the 4th stage. So you can have 6 stages, and you can still have 4-way fine-grained multi-threaded. What else do I want to say? Basically, even the floating point unit was shared among the cores. And this turned out to be one of the bottlenecks. And in Niagara 2, they actually replicated the floating point units. So this is actually really, really wimpy. Right? It doesn't even have a floating point unit, the core itself. OK, if I was talking about a different story, I would talk about the evolution of this. But I'll stop that evolution for now. Maybe another lecture will talk about how these things evolved, basically. IBM, for example, let me give you the basic idea. IBM tried to make its cores much more efficient. So it designed Power 6, Power 7, Power 8, Power 9. It's still beefy, but it's a lot more efficient than Power 4. So it kind of moved toward the direction of smaller cores, but it's not really small in the end. Whereas Sun actually went the other way. It tried to get closer to beefier cores, basically. It added it added run-ahead execution into its core. So it tried to basically overcome the disadvantages of a small core. But then it got bought by Oracle, and then Oracle started designing their processors. But that's a different story. OK, let's get back here. Basically, I've introduced small and large and gave a little bit of history of multi-core to you. So remember what we want. The demands, and the reason they moved towards these different directions, they were really trying to get to a good balance with a single core design between many different workloads, right? Sun, for example, figured out, OK, floating point units, there are a bunch of workloads that require this floating point unit in our core, so we're going to add that. Now they pay the cost of floating point units in all of the cores. Maybe if they had a heterogeneous core, that would be better, but then they made that design choice. Okay. So we have different demands. Going back to the serialized code section, we want one powerful large core. In a parallel code section, we want many wimpy small cores, perhaps, and these conflict with each other. Can we get the best of both worlds? So let's do make some assumptions over here. Let's assume that the small core takes an area budget of 1 and has a performance of 1, and a large core takes an area budget of 4 and it has a performance of 2 for a given piece of work. This is the tile large approach. You get high performance on the single thread, serial code sections. You get 2 units of performance because you can only run that single thread on a single large core, right? But you get low throughput on parallel program portions, right? You can have 2 units of performance in each large core. You get 8 units of performance, unless you do multi-threading in the large cores, which we're not going to talk about right now. Tile small approach, it has very high throughput on the parallel part, 16 units. But when you get to the serial part, your performance is only 1 unit, right? You can only run that serial part on the small core. So actually, that was one of the big advantages of disadvantages of the tile small approach. You would lose performance on the serial part compared to existing single core processors. You have an out-of-order core processor, which gives you, let's say, 2 units of performance. You move into the smaller core, you get 1 unit of performance. And that's never a good thing in the world. So these are actually not successful, as you can see, in the general purpose domain. In very special purpose domains, they may be successful. So the idea is to have both large and small on the same chip. Now, we're adding performance asymmetry into the chip. We're going to still keep the same ISA, instruction set architecture. And that's the idea of asymmetric multi-core, asymmetric chip multiprocessor. This is one example, again, a simple example perhaps. You provide 1 large core and many small cores. And you accelerate the serial part using the large core, so you get 2 units of performance. And you don't do too bad on the parallel part. Instead of 16, you get 12 plus 2, 14. Right? And if you actually add multi-threading on this core, maybe you get closer. But you could do that over here also. That's the beauty of dynamically having this asymmetry. But we're going to talk about static asymmetry. We're not even going to go into the dynamic asymmetry right now. But I think going forward, dynamic asymmetry is much more powerful because you could configure things to look like this, look like this, look like this, look like whatever, right? If it's possible. So the trade-off over there is if you have dynamic asymmetry, you need to be able to add enough configurability into your hardware. And once you add that enough configurability, you're not specializing your hardware for high performance. And maybe you won't get the high performance of a large core when you connect multiple things together. And also, you have this overhead now, right, of configurability. OK, so this is one example of the serial. When you have a single thread, put it onto the large core. When you get to the parallel portion, which usually looks like this, spawn them on the other cores, right? And then when you get to the serial portion, that single thread executes over here. Now, this is a nice picture over here. This is the serial bottleneck, parallel part of the program, and then you get a serial bottleneck again. But it's not always like this. Sometimes you have fewer threads, right? They're aggregating results, and then a single thread doing something, and then spawning more threads. OK, let's look at the performance of this. I've shown this earlier, so I'm not going to harp on this as much. But this is the tile large approach. Serial performance is good. Parallel throughput is bad. Tile small approach. Parallel throughput is good. Serial performance is bad. And this is the ACMP, asymmetric chip multiprocessor. Serial performance is good, and parallel performance is close enough. Maybe. We're going to. And the hope is that if you have 1,000 cores over here, the loss in parallel throughput is not so high. So this thing scales, perhaps, but you're not losing performance on single thread. And you could, of course, think about adding more large cores, why that might be useful, we'll talk about. Or maybe having an even bigger large core if it's possible to do it, right? Given the constraints. So we're going to modify Amdahl's law. I'm not going to talk about this a lot, actually, but there might be a homework problem that you will have fun with related to this. Basically, this is a simplified Amdahl's law for an asymmetric multiprocessor. It assumes that serial portions execute on the large core, and parallel portions execute on both small cores and large cores. And we will keep F as a parallelizable portion of a program. Now, because we have different processors, you have L and S, and we have the speed up of a large processor over a small one, X. This is speed up over a single small core. Now, F, the parallelizable portion, can run on both processors, both the small cores. So you divide the performance with S. And also on the large core, L times X. L, basically, the large cores can give you the performance of, basically X times the performance of a small core. That's why you multiply it by X. And also now you can actually improve the performance of this, right? Serial core, serial part by X, because you can run that serial part on a beefy large core. And now you can plug in a lot of numbers and figure out how the scales, how the curves change. If you have time, maybe we'll go into that. But this is really interesting, actually. Okay, let's get back to this. So now we've covered the serial bottleneck, right? So this is Amdahl's law modified for executing the serial bottleneck on a large core in a heterogeneous multi-core engine. But there are a bunch of other stuff that we didn't put on the heterogeneous multi-core engine. So we're going to look at that. Can we accelerate these parallel bottlenecks as well? And serialized or imbalanced execution in the parallel portion can also benefit from a large core, obviously. Examples are critical sections that are contended, or parallel stages that take longer than others to execute. And the idea is very simple. We're going to try to make it work. Dynamically identify these code portions that cause serialization and execute them on a large core. Talk about this paper first. Well, let me give you the motivation over here, because the motivation is quite strong, actually. Let's take a look at this program that has some critical sections and some parallel portions. Let's assume that if you run it with a single thread, 33% is spent on the critical section. The execution time looks like this. Now, if you parallelize it, the execution time looks like this. When one thread is in the critical section, the other thread cannot be. So you gain performance. It looks good. You don't get perfect performance because you have some critical section inside there, right? Your performance is still bottlenecked by that critical section, so you don't go from 12 to 6. But it's not bad. Now, if you have 3 processors, you again gain some performance, but now your performance is bottlenecked by the critical section. At any given point in time, because I assume that the critical section is 33% of the execution time of a thread, at any given point in time, there is a thread that's in the critical section. And no other thread can be in the same critical section. It's locked, that part, and the other thread reaches it, so it needs to wait. Make sense? Now, if you add more processors over here, you won't be able to improve performance because your bottleneck is serial. What you will get is more waiting. And this is what you will get if you're lucky, actually. Usually, this will go over here because you will add additional communication due to coherence, ping-ponging, overhead, ... But this is ignoring that. Basically, going from 3 threads to 4 threads don't buy you any performance. It actually buys you less performance and a lot of waiting. Right. So you've just added more waiting. That's the reason why the curve either saturates or goes down. Right. That's one of the reasons. Now, let's assume that we magically accelerate the critical section by 2x. Okay, you improve performance with a single thread also. With 2 threads, you improve performance also. With 3 threads, you improve performance. But if you notice over here, your bottleneck is not the critical section still. Your bottleneck is still in the parallel portion. So as you add more threads, you still keep improving performance, right? So going from 3 to 4 threads buys you performance if your critical sections are not the bottleneck in the system. That's why we can improve scalability also by getting rid of these serial sections as much as possible. And that will be our goal. You can increase performance as well as scalability. Scalability is the number of threads at which performance saturates or starts going down. Okay, so contention for critical sections lead to serial execution in the parallel program portion. And this increases with the number of threads and limits scalability. So with MySQL, as I showed you earlier, this is data from this paper actually. That's what you get. And it keeps going down actually significantly. Now, this is not the only effect, critical section. There's also resource contention, load imbalance, everything else that starts accumulating. As a result, you get this kind of bad curve. And if you're a programmer or if you're a system designer, if you're running your system at 32 threads, for example, you're not doing a good job, right? So you should really figure out the best number of threads that is buying you the highest speed up and configure your system or program to run at that best number of threads. Otherwise, you're not really getting good performance, right, if you're using 32 threads to run this program. But that's actually a tough problem also. How do you decide how many threads you're going to launch? How do you know this curve beforehand? Maybe you don't know that curve beforehand, right? How do you figure that out? So that's actually a tough problem. And that's a research topic also. But we're not going to talk about that particular topic. We're going to talk about how to get to this asymmetry. OK, so execution time of sequential kernels, critical sections, and limiter stages must be short. You can say, again, punt the problem to the programmer. Say, it's not my problem, it's the programmer's problem. So I'm going to design smaller cores, and, or even larger cores, and tile them. But the problem is the programmer may not have domain-specific knowledge to optimize a program really well. Even though they may optimize a program for a particular platform, hardware platform, really well. Now, what if the hardware platform changes slightly? This is actually a huge problem with GPUs, for example. You optimize your program for a GPU, and you get the highest possible performance. Now you lost all the portability to another GPU, right? Because it's just a little bit different, maybe a lot different, right? So this variation, if you punt it on the programmer, then programmer goes crazy. Now, the really smart programmers, of which there are few in the world, or a very small fraction. I don't want to call it smart, but those are people that are sort of smart and also have a lot of experience in doing this, right? But most of the world is not like that. And they have limited resources, right? Hardware is expensive, but software development is also very, very expensive. So if you punt on the programmer, you have a problem. And also, you run into this very unfortunate trade-off. You may push performance, but this may come at the expense of bugs. Because the programmer can say, oh, I'm going to reduce this critical section, so let me get rid of all of these instructions in the critical section. If you get rid of the right instructions, maybe that's good. But if you get rid of the wrong instructions, now you get bugs, right? Even though you need to really have a critical section there, you don't anymore because you're really pushing for performance. And that's really the art and difficulty in the parallel system design, that you really want high performance without making the programmer write buggy programs. OK, so our goal is a mechanism to shorten serial bottlenecks without requiring programmer effort, or minimal programming effort. And the idea is very simple. Accelerate the serialized code sections by shipping them to powerful cores in an asymmetric multi-core processor. Basically, the hardware software cooperatively ships critical sections to a large, powerful core in an asymmetric multi-core architecture. The benefit is you reduce serialization due to contended locks. This reduces the performance impact of hard-to-parallelize sections, and the programmer doesn't need to heavily optimize the parallel code. Right? So hardware does it for you, or the system, because we're going to require some help from the software also. It's very difficult to automatically do this, because automatically doing this requires the programmer to program, requires the discovery of these critical sections automatically. And that's another problem that fascinated some people. How do you discover these synchronization critical sections automatically? And if you discover them, then you can get rid of all of these bugs, right? But that's a very tough problem, it turns out. It turns out it's much easier if people follow disciplined programming languages and say, mark the critical sections. This is the beginning of my critical section. This is the end of my critical section. And if you do that, the hardware has a nice grain, let's say, nice thing that it can ship to somewhere else. Right? So I think that would be the burden on the programmer for this case. So let's take a look at, I'll cover this and then we'll take a break. Are you guys tired? Okay, I think we should take a break soon, but I want to not finish in the middle of the idea. But basically, assuming that somebody marks your critical sections, for example, you're inserting into a shared priority queue or a heap, and no other thread should read from it or insert into it. Clearly, that's a critical section. And somebody has marked them. We're going to add this critical section request buffer in hardware such that you can accumulate critical section requests in this large core. And we have these small cores. And critical sections will be executed only on the large core. When processor 2 encounters a critical section call marked with an instruction, it sends a critical section call request to the critical section request buffer. And processor 1 and queues them in a FIFO manner. When processor 1, when this gets to the head of the queue, the processor 1 executes the critical section. Now shared data remains in processor 1's caches. It doesn't go anywhere else. That's one benefit. And when it's done, it sends the critical section done signal. It also ensures that all critical sections are executed over here. As a result, things are serialized, right? Which they should be anyway, because these are critical sections. Okay, so how do you make this work? So this is a small core. Let's assume that you have some computation. This is the critical section. You take a lock. You compute something in the critical section function. You unlock it, and then print the result. Now we're going to execute it cooperatively between multiple cores. The small core needs to communicate the inputs to the critical section. So there's some data that needs to go into the critical section that's generated by this thread over here, right? So that needs to be sent to the large core. So there is some communication overhead now. This input parameters need to be sent, and we're going to use stack-based communication over here. You push it onto the stack, and then you have the special instruction critical section call with lock X at a target PC, starting point of this critical section, and send it over the interconnect to the large core. It gets queued in the critical section request buffer. At some point, when the large core gets to executing it, it acquires the lock just for correctness. And there are reasons why you may want to do that, but I'm not going to go into that. The paper explains that. So whenever you're optimizing things like this, you need to be very careful about deadlock, right? You need to ensure that you're the only one who's executing the critical section. You need to ensure you're obeying the program semantics. That's why we need to acquire that lock. But the details are in the paper. And then you pop the result from the stack, not the result, the input parameter from the stack, execute the critical section, push the results onto the stack such that this core can read it and continue, release the lock, and then execute this critical section return instruction, which sends a critical section done response to the small core, which pops the result and then prints the result. So of course, somebody needs to generate this code. Who is that somebody? If the programmer is programming nicely with libraries, using libraries to acquire and release locks, it could be actually incorporated into the compiler of that library, right? So it could be relatively automatic. If the programmer is not programming nicely, then you have a problem. And actually, a lot of expert parallel programmers try to optimize these critical sections so they don't program nicely. They use all of these condition variables and stuff that they do their own synchronization. You can argue maybe they don't need it, or maybe if they're so expert, they're going to insert this code themselves, right? Which is possible. Okay, maybe this is a good place to stop before going into the details of this. Let's take a 7-minute break, and then we'll come back, talk about some of the issues with this idea. Okay, let's continue. So remember, this is what we were doing, executing critical sections on a large core and dedicating that critical section execution on the large core. We're just exploring the idea right now that dedication may or may not be a good thing, right? So one problem that this idea causes that otherwise doesn't exist if you execute the critical sections in the local cores is false serialization, right? So if all critical sections get shipped to the server that executes those critical sections, server is the large core in this case, you can serialize independent critical sections, right? So you have the critical section that's protected by lock X, another critical section that's protected by lock Y, and they may have nothing to do with each other, right? But they both get shipped to the large core, and large core can execute only one critical section at a given time. If these critical sections were executed in the small cores, they could be executed in parallel, right? So that's a problem. So how do you solve that problem? One solution could be having multiple large cores, right? And then you ship different critical sections to different large cores, which is not a terrible solution, actually, which we will talk about, if you have enough area in your multi-core system. Another solution could be having multi-threading in the large core, and one thread handles one critical section when the other thread is handling the other critical section. Now, maybe you don't get the full acceleration benefit because the threads are contending with each other, as you know, in a multi-thread engine, right? So the solution in this paper is reactive. Basically, you selectively accelerate critical sections. Let's take a look at that. You keep track of false serialization And if it's happening a lot for a critical section, you tell the small core, don't send me the critical section. Right? So let's take a look at this. That's why it's a reactive solution. This is a critical section request buffer in the large core that we saw in an earlier slide. Let's say we have these saturating counters for critical section A and critical section B. If you have a critical section called A, we decrement the counter because it's fine. It's not delayed by any other critical section. But if we have a different critical section totally independent of A that gets queued, its counter gets incremented because it gets delayed. There's interference between critical section requests, right? Because this large core is a shared resource now that's being interfered on by these critical sections. So this B is delayed. As a result, its counter is incremented. And if that counter is greater than some value, the large core sends a message to the small core saying, I'm not going to execute your critical section. Don't send me this critical section for a while because it's getting serialized all the time. Right? So that's one protocol, for example. The bigger point over here is whenever you have a server like this, I call this a server, because essentially what we've done is remote function call, right? This is really a distributed system concept. We're really sending a remote function call to a server that's executing it on behalf of the client, which is the small core, and the server is returning the result. You're marshalling the input, which is all of this stuff, plus pushing stuff on the stack, and the server is executing it. Whenever you have a server that's contended by multiple clients, you have this problem, right? Some clients may get denied service for a while, and you want to solve that problem. Okay, so this is not a bad solution, actually. This paper analyzes that. But if you have a lot of critical sections, this may be a bad solution. Let's look at the trade-offs. So the plus, you get hopefully faster critical section execution, right? So far, I've assumed that this large core executes the critical section faster, but that's not guaranteed. What if the critical section is very much bottlenecked by the memory system? Maybe a large core is not that efficient, right? What if the critical section has a lot of dependencies? The large core doesn't buy you much, right? Because the large core is exploiting instruction-level parallelism. So this is not always true also. So ideally, you need to estimate when you get benefit from this. The other plus, big plus, is shared locks stay in one place, which is the large cores, hopefully large caches. As a result, you get better lock locality, no ping-ponging of the locks. And shared data stays in large cores, large caches, also a better shared data locality, less ping-ponging again. That's the benefit of localizing execution on shared data. Now, the minus is large core is dedicated for the critical sections. As a result, parallel throughput is reduced. When you have a lot of parallelism, you cannot use the large core. And you have this transfer overhead, critical section call, critical section done, right? That adds overhead that didn't exist before. Actually, the ping-ponging overhead gets transformed to this overhead, right? Here you are communicating data. Here you're communicating code or computation. You're not sending the code because this is shared memory. Large core already has the code in its memory. You're really sending stuff to enable the execution of the code. Hopefully, this is much smaller than shared data and shared locks. And the analysis indicates that this is much smaller, actually. So one other trade-off is, actually, you can think of this as analogous to the locks themselves, right? The data itself, shared data, stays in the large core caches. That's one upside. But now private data needs to be communicated. The input that the thread produced, this A, for example, over here. No, let's go back. Yeah, you need to push the inputs. And there may be many inputs into the critical section that are computed locally by this thread, right? Okay? That data needs to be transferred to the large core, so you get worse private data locality. Whereas if the thread stayed, the critical section stayed in the small core, you would compute that thread private data, and then you would use it in the small core. Shared data may need to come from somewhere else. Okay, so there's a trade-off between shared data locality versus private data locality. And as a result, you have a bunch of performance trade-offs. So the first trade-off, fewer parallel threads versus accelerated critical sections. You get loss in parallel throughput, basically, but in the long run, this may not be bad, assuming the number of cores on chip increases. The fractional loss in parallel throughput decreases because you have only one core dedicated. So if you have, let's say you have a 64-core, you have an 8-core chip, 8 small core chip, and 4 of those small core areas are taken by a large core, your loss in throughput is 1/2, right? 50% of your throughput you lose. Because out of the 8 possible cores that you can allocate to small cores, 4 of them you're allocating to the large core. But if you have 1,000 small core area chip and you're dedicating 4 of those to a large core, you're losing throughput only 4 out of 1,000, right? 4%, less than 4%. Wait a second, 4 out of 1,000 is less than 4%. That's good, I can still do calculation. So as the number of cores, small cores increase on chip, this becomes less of a problem. Of course, you can argue that maybe we want bigger cores in that case, bigger large cores, but designing them may be hard. Okay, overhead of critical section, call critical section done versus better lock locality. You avoid ping-ponging of locks between caches by keeping them at the large core, and this turns out to be a good thing. This is less of an overhead because ping-ponging is a lot. Okay, and the last one is you get more cache misses for private data versus fewer misses for shared data. That's an interesting trade-off, actually. So I'll ask you a question. What is the working set size of a shared data versus private data? Which one is larger, you think? Any thoughts? So you have a working set size of shared data. Shared data means things that many threads operate on, versus private data, things that only one thread operates on and inputs to the critical section. And which one is larger in a critical section? Any idea? The answer is it depends, actually. Basically, it really depends on how did you write the critical section. If it's a really well-written critical section, there should not be much private data operations inside the critical section, right? But let me give you an example. That's not always the case also. It depends on the problem that you're solving. So let's assume that this is a heap, priority heap. You're inserting something. The thread produces some data that's input to the critical section, and whenever you're trying to insert it, you're touching a bunch of shared data. And you need to protect the shared data structure, right, whenever you're touching it. Nobody else can read it while you're modifying it. Right? If everybody is reading it, there's no problem. You don't need to protect it. But if somebody is writing to it, then you have a problem. So let's say we are inserting this. We touch a lot of shared data, right, to be able to insert this little amount of private data. So this is one example where the shared data that you touch inside a critical section is much larger than the private data that you touch. And that's usually the case. And ideally, again, you want to just protect the private data. You don't want to do operations on only, you want to protect the shared data in the critical section. After you acquire the lock, you want to do a minimum number of operations, right? That's necessary to manipulate the shared data structure. If you have an operation that's only on the private data, that can go out of the critical section, right? Because that has nothing to do with the shared data. Make sense? Only when you're touching the shared data, that should be in the critical section. But it turns out programmers are conservative because of the programming ease and bugs trade-off. They sometimes have operations inside the critical section that have nothing to do with the shared data. So they protect these operations unnecessarily, so you have a larger critical section. As a result, more contention in the system, and also a larger amount of private data that is touched in the critical section. And whenever you're actually trying to reduce the critical sections, you really want to get all of those private data manipulations out of the critical section. So the answer is it depends. The paper has analysis. It depends due to the nature of the problem. In this case, for example, if you're touching a huge heap, yeah, probably shared data that you touch is bigger than the private data. But it also depends on what you're inserting, right? What if you're inserting many, many nodes at the same time? Then your private data may be a lot also. Okay. So basically, cache misses that you have reduced if the amount of shared data is greater than the private data, or shared data misses is greater than the private data misses. And this problem can be solved if we have time, I will talk about a solution that's much more general than just accelerated critical sections, which is really interesting, actually. Okay, and that's part of the solution. Okay, let's look at the performance of this. Now we've designed the system. We evaluated through simulation again. Actually, this turns out to be a much harder simulation than what you guys are going to do in your lab 3 and lab 4. Because you need to actually take into account all of these synchronization, right, in the program. And somehow you need to communicate it and you need to simulate it, right? It's not easy. Okay, so we're going to evaluate this SCMP, symmetric small core multi-core, asymmetric multi-core where the critical section, not the critical section, but the serial portion of the program, serial bottleneck executes on the large core, and accelerated critical sections, not only the serial bottleneck, but also the critical sections execute on the large core. And this is a simulator. You can read the paper. How do you find some workloads, basically, that you need to evaluate also. So there are a bunch of things over here that you can read and find out in the paper. I'll give you some of the key results. So this is actually an area that you need to be very careful when you're doing performance evaluation also, because it's not like you run a single thread and you get performance out of it. You have multiple threads. How many threads do you run becomes a question also, right? So let's take a look at the baseline over here is symmetric multi-core, 32 small cores. Accelerating sequential kernels, this is basically accelerating Amdahl serial part. On an ACMP, you have 1 large and 28 small cores, and in this cyan thing, or turquoise thing, I guess this is turquoise, not cyan, right? Yeah, turquoise. Okay, basically you have 1 large core and 28 small cores, but the large core is executing only the serial part. So even the serial part is significant in some of these workloads. As you can see, this workload gained 40% performance, quicksort, parallelized in some manner, gets 40% or so performance, almost 50%, if you dedicate the execution of the sequential part on the large core. Right? Now, if you accelerate critical sections, as we've discussed, you get a lot more performance, because it turns out these programs on the left over here use coarse-grained locks, meaning the programmer didn't spend a lot of effort to optimize these programs. They basically said, well, one way of parallelizing a program is when you start a thread, you take the lock. And then when you end the thread, you release the lock. Right? Now, all of the threads are serialized, right? That's really simple for the programmer. But of course, you don't gain any benefit from parallelization. Everything you consider shared data. So you can think of the extreme of coarse-grained locks as that way. But programmer didn't optimize as much. As a result, there is a lot of lock contention. And if you accelerate the critical sections, you get a lot of benefits on some workloads over here. But here, programmer optimizes these workloads. These are some of the databases, web cache, for example. They have fine-grained locks. There's still lock contention, because the critical sections also depend on not only how much you optimize, but also the sharing behavior of the programs. As a result, you get smaller benefits, but some of these benefits are reasonably large still, like about 20%. In these workloads. IP lookup is a router workload where you actually have many threads that are trying to look up IP, and you have a shared or change the router configuration. As a result, you actually have critical sections over there. Okay, so the harmonic mean is over there. You can look at the numbers in the paper also. So there are cases actually where dedicating a large core loses performance, as you can see. That's the loss in parallel throughput. And you don't gain much because you make up only very little of that loss. As a result, the gain that you get by accelerated critical sections over here is relatively small. So there's another thing that I didn't say over here. So basically, accelerating critical sections gets you a significant performance improvement. But the comparison here is equal area, and the number of threads is set to best number of threads. Now, what do I mean by that? You need to pick a point, the best operating performance point for each configuration and each workload. So for example, PageMine, you compare PageMine performance on 3 architectures, right? Symmetric multi-core, asymmetric multi-core with accelerated sequential kernels, and asymmetric multi-core with critical section acceleration. Those have all different operating points that's best for them, right? In one, you may need only 16 threads. In the other one, the performance saturates maybe only at 16 threads. In the other one, the performance saturates at 14 threads. In the other one, the performance saturates at 18 threads. So the comparison is made by comparing those best points. So what do I mean by those best points? So whenever you compare parallel performance, you should really look at things like this. Basically, page minus over here. You have 32 cores, let's say, chip area in terms of small cores. And this is the speed up over a small core on the y-axis. 1, everything starts at 1. As you can see over here, the symmetric multi-core curve looks like this. It's underneath the red one, which is accelerating the serial part of the program. So the performance is best over here, and the speed up is 3. So with about 4 or 5, maybe 7 over here, 7 threads or 6 threads, you get a performance improvement of a little bit below 3. And that's the comparison point for ACMP. You don't want to really compare everything at 32, right? Because 32 threads is not the best operating point for this workload. If you're choosing 32 threads, then you're not doing a good job choosing the number of threads for your program. But as I said earlier, this is not an easy problem also, because it's very data set dependent as well. So as you can see, that's where the PageMine performance is. Accelerating the critical sections actually improves the performance as well as scalability, as you can see here. Your performance goes up to 4x compared to a small core, and it starts saturating a little bit later at about 8 threads or so over here. So performance improves and scalability improves. And it looks like, for example, here, Puzzle was very much bottlenecked by critical section performance. The scalability curve looks like this. If you actually accelerate the critical sections, you keep scaling. With 32 threads, you get about 6x performance. It's still not linear scaling, but still much better than what was there before, right, with symmetric approaches. And you can see other things also. Some performance still starts saturating after some point, as you can see in some workloads over here. So the scalability of about 7 of these workloads actually improves. And this traveling salesman problem seems to be one of the more scalable ones, as you can see over here. That's actually true for the baseline machines also, but the critical sections, if you handle them well, you get better, even better performance. Okay, I've already said everything over here. Basically, accelerating critical sections by executing them on a powerful core gets you better performance. So let's try to generalize the idea now, because critical sections is not the only thing. It may be an important thing. But can we somehow accelerate all bottlenecks by accelerating them on a large core? We're going to talk about the idea of, well, that's the paper, the bottleneck identification and scheduling. And we're going to try to accelerate all of these things. Serial portions, we've already accelerated, so that's easy to do. Critical sections, we've also discussed this, but there's one problem with the critical section that we've done so far. We're shipping all of the critical sections to the large core, right? That's not necessarily a good idea, because the critical section may not be contended. If it's not contended, why do you ship it to the large core? You get locality benefits. That's one good answer to my question just now. But you don't get acceleration benefits necessarily. Barriers, as we've said, these are important synchronization points, and pipeline stages. Different stages of a loop iteration may execute on different threads, and the slowest stage makes other stages wait. So that becomes on the critical path. So basically, things can be on the critical path. When only one thread exists, it's clear that it's on the critical path of execution, right? Critical sections are on the critical path of execution if they're contended. Barriers, the last thread arriving is on the critical path. So wouldn't it be nice if we can find out the critical path or predict the critical path of a program and ship that critical path to a place that can accelerate it? Right? So, and these critical paths change over time. Let me give you a toy example. You can come up with any toy example, and you'll clearly find that people do similar things in the real world. There's so many programs there, out there that whatever toy example you come up with will map to some program in the world. But this is one example just to show that bottlenecks change over time. Basically, we start with a full linked list, and we have many threads that are going to execute the same code. And basically, we remove an element from the list, do some computation, and insert the element into another list, list B. And let's assume that we have many threads that are doing this. As a result, this is a critical section, this is a critical section. The computation on that private data is not a part of the critical section. You could make this part of the critical section. Now your critical section is longer. unnecessarily. So we're going to look at the behavior of this. If you look at the behavior of how many threads are waiting for this lock at any given point in time versus this lock at any given point in time, initially many threads are waiting for this lock because this is a full linked list, right? You traverse it, it takes time, and as a result, you cause a lot of waiting for other threads. All of them are trying to do the same thing. They're trying to remove stuff, and later they're going to try to add stuff to this linked list. As a result, this lock is not contended, but this lock is contended. After some point, this list becomes empty, so nothing happens over here, and this list becomes bigger, fuller. You keep populating it. As a result, this lock becomes contended, and there's some point where both of the locks may be critical, right? So this behavior exists in real programs. It's a cooked up program, just to show this. But limiter locks actually change. Limiter critical sections change. And this is a real example from one piece of, one part of the MySQL database for two different locks. You're opening the database tables, and this is the lock for the log. Usually you log stuff that you do in a database. And it turns out there are some cases where the log lock is the bottleneck. Bottleneck defined as the number of threads that are waiting for that lock at that point in time. And at other points, the bottleneck is something else, right? The lock open. There are 14 threads that are waiting. And we're assuming the maximum number of threads are 16 over here. And if you look at the time scale over here, it's really fine-grained. This is millions of cycles, right? So it's much lower than an OS scheduling interval. So you could always think, oh, it's a software solution to this. Maybe the OS deschedules. OS tries to figure this out and tries to schedule things better, but it's very hard to do at this fine granularity interval. Maybe you can figure out other patterns at the higher level, software level, and try to do scheduling such that you don't run into some of these contention issues, but that's a different topic. So the idea of bottleneck identification and scheduling is built based on that. Basically, thread waiting, this is very fundamental. Thread waiting, a thread that's waiting and doing nothing, spinning on a lock, reduces parallelism and is likely to reduce performance. And it has adverse effects on power, clearly. Code causing the most thread waiting is likely on the critical path. So that's the prediction, if you will. Estimating the critical path perfectly is a very tough problem. It's actually an NP-complete problem. We're going to try to do that, not online. We'll do it offline, and I'll show you an example later on, not as to how to do it, but an example showing how good we are in estimating whether we're on the critical path. So basically, the insight is that code that's causing the most thread waiting is likely on the critical path. And the key idea is to dynamically identify bottlenecks that cause the most thread waiting and accelerate them using powerful cores and asymmetric chip multiprocessor. So it consists of actually, this is one way of doing it, but I think you need hardware-software cooperation. It's very difficult, as I said earlier, to do it purely in hardware. It's very difficult to do it purely in software because of the granularity. Compiler, library, and hopefully not the programmer, annotates the bottleneck code, potentially bottleneck code. It implements waiting for bottlenecks. And then somebody inserts these BIS instructions that are special, which enable the hardware to measure the thread waiting cycles. How much contention does each bottleneck cause? And hardware automatically finds those things that cause a lot of the contention and accelerates the bottlenecks that cause the most contention. Let's take a look at these two different components. So this is a critical section. Basically, this is the loop that's waiting for the critical section, and people have tried to do a lot of code optimizations to minimize that waiting, for example. We're not going to talk about that. And there are a lot of synchronization primitives that try to minimize the overhead over here. But if somebody has acquired the lock, you basically cannot enter. That's the fundamental principle of a critical section, right? This is the critical section until that person releases the lock. So you need to do some sort of waiting over here. So what we're going to do is outline this as a function. Now we have a function called to a potential bottleneck. And we're going to give it an ID. This is bottleneck ID. And somebody's going to number those IDs, compiler, in the end. And it has a target program counter. So this is the critical section call now. And if the programmer is, again, programming in a disciplined manner, this already exists, actually, because you program using libraries, except these instructions don't exist, of course. Not yet, at least. Although there are some interesting instructions that may be used for similar purposes. OK. So we're going to add that bottleneck ID such that we can differentiate between potential bottlenecks, potential critical section in a program. So here, this is usually how waiting is implemented in existing systems. In fact, x86 has an mwait instruction, for example, that you can use. There are other ISAs that have different instructions. So we're going to delineate things with bottleneck call and bottleneck return, such that the hardware can keep track of things. But there's one thing that we're going to change over here. Hardware will actually keep track of this waiting. So we'll add a special instruction called bottleneck wait. While watching that address that's changing by someone, basically, before, when you release the lock, you change this address such that somebody else who's polling on that address actually sees that, oh, now I can go into the loop, go into the critical section. So we're going to change that such that you have this bottleneck wait instruction associated with the bottleneck and the address. And when this program is executing the bottleneck wait instruction, it's basically going to increment thread waiting cycles. So this is used to keep track of waiting cycles because you're waiting for this bottleneck over here, bottleneck BID. Okay, and this is used to enable acceleration. Now you have a nice delineation of the critical section. Now you can do this for barriers. So this is an example of a barrier. You enter a barrier, and while not all the threads are in the barrier, you wait. And once this becomes not true, you exit the barrier, right? And this is the bottleneck call. Basically, this is how you run for the barrier. This is a parallel part of the program. You have code that's running for the barrier, and once you're done, you return, and then you enter the barrier. So basically, the thread that gets here earlier is going to increment that bottleneck ID's thread waiting counters. Okay, and this is a pipeline stage. This is just to give you a high-level code example with bottleneck instructions. Basically, this is the call. Basically, this is the pipeline stage that you're implementing. Since this is a pipeline parallel program, you have an input queue and you have an output queue. And the thread that's in the previous stage feeds into this input queue. If the input queue is empty, that means that the previous thread is not doing its job. You're waiting for it, right? It's somehow not feeding you with data. As a result, it's the bottleneck. So the previous thread that's supposed to feed into this queue, that its thread waiting cycles get incremented. If the destination queue, if the output queue is full, then the next thread is not doing its job, perhaps, at least as fast as you want it. As a result, that's the bottleneck. So you increment the cycles, thread waiting cycles that way. Okay. Okay, so let's take a look at, now that we added these instructions, bottleneck call and bottleneck wait, to account for thread waiting cycles and to delineate the critical sections or potential bottleneck parts of the code, what does the hardware do? So let's look, basically, identification of the bottleneck and acceleration are actually independent tasks. Acceleration can be accomplished in multiple ways. When you get to a bottleneck, for example, you can increase the core frequency and voltage. That's another way of adding asymmetry. As we've discussed, you can use this for driving scheduling decisions in the memory controller. If the memory request is coming from a thread that's designated to be a bottleneck at that point in time, you prioritize that. Or you migrate to faster cores in an asymmetric multi-core, which is what we're going to look at over here. Or you do all of them, right? That's another possibility. Because presumably, this is your bottleneck at that point in time. So how do we measure thread waiting cycles for each bottleneck in hardware? I'll do this pictorially. Basically, we're going to add some hardware bottleneck table that keeps track of how much thread waiting cycles each bottleneck that's executed has caused. Of course, it's a small table. You need to optimize it, and you need to have an eviction policy if you don't have enough entries, ... So you add complexity, basically. So let's assume that a small core gets to a bottleneck wait instruction. It's waiting for someone else to get out of this particular bottleneck at 4500. It sends that to the bottleneck table. Bottleneck table records the bottleneck ID, and it increments the waiters, and it starts counting. You could, again, do this counting every cycle or every n cycles. There are a lot of design choices here. And while the core is waiting, it keeps incrementing the bottleneck ID's thread waiting cycles. Now, another core starts waiting. The waiters becomes 2, so you increment thread waiting cycles by 2 every cycle. You can aggregate all of these increments, of course. When this core stops waiting, it sends saying, I've stopped waiting. I've entered the critical section, let's say. So the number of waiters gets decremented. So you keep incrementing thread waiting cycles by the number of waiters. And at some point, this core also stops waiting, and its number of waiters becomes 0. So that's how you keep track of how many cycles of waiting did this bottleneck cause, right, with those instructions. And you can get a pretty accurate number depending on how much corners you cut in terms of the granularity at which you're quantizing or incrementing these counters. Okay, so that's not that bad. That's the beauty of adding another instruction, right? Now, what do you do with it? Basically, let's assume that we have these two bottleneck IDs with these two different thread waiting cycles. The core gets to a bottleneck call at 4600 bottleneck ID. It sends to the bottleneck table and asks the bottleneck table, where should I execute it? The bottleneck table says, checks the thread waiting cycles of the bottleneck and compares it to a threshold, which could be determined dynamically. It's less than that threshold. The bottleneck table says, you're not executing something important, so execute it locally. And the small core goes back and executes it. And later it gets to a bottleneck call 4700, asks the bottleneck table, tell me where to execute this. And the bottleneck table says, oh, this is something important. You'd better send it to the large core, right? Execute it remotely. And then small core prepares it and sends it to the large core. So large core now has a scheduling buffer. Remember, this was a FIFO in the critical section request buffer. Here, we're going to try to do the scheduling such that the most important bottlenecks are prioritized over others. So the bottlenecks that have higher thread waiting cycles are prioritized, scheduled earlier. So it's very similar to accelerated critical sections now. You send the bottleneck ID, program counter, stack pointer, which core you are, ... And you get queued in the large core. And the large core executes the bottlenecks in order of which ones are more important. And when it executes the bottleneck return call in the code that you've seen, it basically sends a request, sends a done signal saying, I've executed your bottleneck, now you can continue. Does that make sense? It's pretty simple, right? Now, one of the issues over here, whenever you design a system like this, you have problems because now you need to communicate with this bottleneck table, right? And that turns out to be a bottleneck in itself, not communication. So you don't want to replace a bottleneck with some other bottleneck. So how do we solve this problem? Basically, you need to cache portions of this bottleneck table inside the small core, such that you can make the decision quickly, locally, to decide whether you're going to execute the bottleneck here or there. That's the acceleration index table. Basically, with a given bottleneck, should I execute it here or should I execute it there? Local decisions. Local decisions are better than decisions that require coordination. Basically, once in a while, the bottleneck table updates these acceleration tables. It broadcasts to the smaller cores to describe where should a particular bottleneck get executed. Now, this is becoming a relatively good substrate because you could actually say, oh, this bottleneck should get executed in large core 25 over here, right? Essentially, you're the coordinator for a distributed system with this bottleneck table. Okay, I won't go into a lot more other detail, but basically, there are some basic mechanisms. You still need to deal with things like false serialization over here. You need to preemptively accelerate some things, especially if you're running toward a barrier. It may be too late once you determine that everybody else reached the barrier, right? So you really need to be a little bit preemptive. Barriers are actually a little bit odd in that sense because once you determine that you're the bottleneck thread, it may just be too late, right? You need to do something better than that. So if you have actually programmed semantic information that you can feed into the barrier, saying, for example, a unit of progress for each thread and how much progress that each thread has made compared to how much progress it needs to make to get the barrier, that's very useful. For example, if you need to finish 100 iterations to get to the barrier, and if you know that information somehow, if you communicate it to the hardware, then the hardware can keep track of how many iterations you made progress for, how many iterations you've done so far, and that way you can preemptively accelerate. This is very, very similar to what we've discussed with accelerators, right? When we talked about memory scheduling. Each accelerator has some work to do, some number of memory requests to service to achieve a frame rate. If you know that information in the memory scheduler, you can keep track of how much progress the accelerator has made and you can schedule things accordingly, prioritize the accelerators that are lagging. Very similar. Prioritize the thread that's lagging, and if you know information beforehand saying, oh, this thread has this much work to do, and I've done only this much progress, then you can do much more preemptive scheduling. It's beautiful, actually, I think. So support for multiple large cores, I'm not going to talk about that, but multiple large cores actually helps if you have multiple bottlenecks at the same time. Okay, what's the hardware cost of this? You should read the paper. I'm not going to go into detail. It's not a lot of hardware. It's really the complexity of the hardware that matters in these kind of ideas in general. And also, we need to change the software here as well, right, to add those function calls and instructions. But the hardware cost is low. Complexity may not be that low. And you need to guarantee forward progress. So you should always be asking the question, oh, sometimes we're executing the bottleneck here, sometimes we're executing the bottleneck here. Are there any deadlock issues? We're prioritizing the bottlenecks based on the thread waiting cycle count. Are there any starvation issues? You need to solve all of those to make it work. But there are trade-offs, and trade-offs are similar to accelerated critical section. You get faster bottleneck execution versus fewer parallel threads. You get better shared data locality versus worse private data locality, again. You get benefit of acceleration versus migration latency. So we've discussed these, actually, earlier. We're going to look at this in a little bit. But this is actually interesting. Migration latency is actually usually hidden by waiting. That's good, unless the bottleneck is not contended. So you're basically migrating the bottleneck, but somebody else is waiting for it. So that latency is, you're not losing it, right? Unless the bottleneck is not contended. So you don't want to ship something that's not contended to a large core, because you don't need to ship it. And you're contending in the large core for other important things. So it's very important to determine what's important and what's not important. What's on the critical path and what's not on the critical path. Okay, this again gets simulated. Again, this is not an easy simulation. If you want to do the simulation, let me know. It's fun, but it's not easy. And again, similar application. So these are some details. This is the large core and this is the small core, we assumed. And of course, you need to simulate the on-chip interconnect for this. You cannot assume that the on-chip interconnect is instantaneous, right? Then you have a big problem. You're not doing a good simulation in that case. Okay. Okay, this is the baseline. This is accelerated critical sections. So it turns out accelerated critical sections accelerates only critical sections and Amdahl's serial portions. It's applicable to multi-thread workloads, but it doesn't do anything about the barriers, right? There's also other work that's looked at feedback-directed pipelining. The idea over here is software determines periodically by profiling what are the slowest pipeline stages in a pipeline parallel program. And you can do this by actually instrumenting these queues, right? How many times whenever you checked your input queue, it was empty? How many times when you check your output queue, it was full? You could actually aggregate this at a coarse granularity, communicate this to the operating system, and the operating system schedules the things that are bottlenecks on the large cores, right? That was the idea in an earlier work. So we're going to compare to that also. So this bottleneck acceleration is general because it can be applied to any kind of bottleneck. As long as you insert these bottleneck call and bottleneck wait instructions, you could actually put it in arbitrary parts of the code, right? You just need to be careful about when you decide you increment the bottleneck wait. So this is the performance. This is speed up compared to asymmetric multicore, accelerating the critical sections only. We don't have symmetric multicore here. This is accelerated critical sections or feedback-directed pipelining, depending on what workload you're using over here. So that improves performance. That's good, as we expect. Sometimes it reduces performance because of the loss in parallel throughput. And that bottleneck identification and scheduling actually improves performance over both of them. So these are the workloads where ACS, critical sections, are more. And limiting bottlenecks actually change over time in some of these workloads, as you can see. So this is where, these are pipeline parallel programs over here. But here you get significant performance benefit because limiting bottlenecks change a lot over time. There's a lot of dynamic behavior. Here you get performance improvement again. But here there are a lot of barriers that are limiting. So these workloads tend to be bound by barriers. As a result, you get I think this is a multi-grid simulation, if I remember correctly. But basically, you synchronize at the end of the simulation boundaries, and as a result, because your work is imbalanced, you have a lot of barriers, and those are your bottlenecks. These works cannot accelerate those bottlenecks, but if you actually use bottleneck calls by bottleneck weights, you can accelerate the threads that are running for the barrier. Okay, and that's, you can read for more detail. And it improves scalability also, clearly, whenever you are dealing with contention. So one of the benefits of BIS over ACS is it's not sending non-contended critical sections to the large core. As a result, it's also more efficient. So let's look at what I promised to you, which is, why does this work? This is actually an interesting question. After you have a mechanism, it's always good to ask, why does this work? So this is our attempt at that. This is execution time. And the bars plot the fraction of execution time spent on predicted important bottlenecks. Basically, what fraction of the time are you utilizing the large core? Right. In ACS and FTP, it's about this, basically, 45%. You're spending 45% of the time on predicted important bottlenecks. They may not be the bottlenecks. In BIS, you're actually increasing that because you have more bottlenecks that you're taking into account. It's about 70 or 80% of the time, right? Now, you're not always doing this on bottlenecks that are really the bottlenecks. So if you actually run your program backward, after you have an execution, and if you go and trace backward, you can figure out what threads are on your critical path, right? So if you go back and try to map whether or not you're accelerating those threads that are on your critical path, you can map, you find that these are the actually critical portions of the execution time that are mapped to the large core. So the green parts. Basically, with accelerated critical sections or feedback-directed pipelining, you're covering about 39%. Basically, if coverage is a fraction of program critical path that is actually identified as bottlenecks, about 39% of the program critical path is executed over here on the large core. And with something like bottleneck identification and scheduling, you're increasing that. Basically, the coverage of critical path increases. Because you should probably think about how to do this study fully. And accuracy means these are the identified bottlenecks on the critical path over total identified bottlenecks. So this, for example, this here, let's take a look at over here only. It finds that about 80% of the execution time is on the critical path. But that's not true for this portion. That's true for the green part. So its accuracy is about 73.5% in identifying the critical path. Its coverage is 60%, which means that we're not identifying 40% of the program as bottlenecks, even though there must be some sort of bottleneck over there, right? And if you accelerate it, we can get better performance. So there's significant potential. And also, the study is not easy to do because if you actually accelerate a bottleneck, your critical path changes, right? It could change, at least. If you remember when we talked about this, when we talked about parallel application memory scheduling, if you accelerate one thread a lot, now another thread, another critical section may become the bottleneck. Right? So it's actually hard to do this study. You need to think about this a little bit as to how to do this perfectly. Any questions? There's actually a lot of depth in this slide than this slide shows. Okay, so let's take a look at some scaling results. It's always good to look at scaling results. Basically, what happens with more small cores. If you have more small cores, it turns out contention due to bottlenecks actually increases because you're having more sharing. And loss of parallel throughput due to the large core reduces. So it's good for BIS in 2 dimensions. As a result, performance improvements actually get larger if you actually accelerate the bottlenecks. Because contention increases and you're losing less by dedicating a core for bottleneck acceleration. And if you actually have more large cores, you can now accelerate independent bottlenecks without reducing parallel throughput because hopefully you need to have enough cores. So you get performance improvement, but it's not as high as adding more cores. Okay, you can look at the paper for more detail. Okay, we've covered all of this. So basically, the takeaway is we would like mechanisms like this. We would like to provide fine-grained bottleneck acceleration with no programmer effort. Because that enables much easier parallel programming because the programmer doesn't need to deal with these bottlenecks as much. Of course, the difficulty is now, again, like a lot of other things we've covered in this course, it's a trade-off between the programmer and the microarchitect or architect. Now a lot of burden is on the architect. The architect needs to make it work, right, for the programmer. Okay, so that's the paper. You can look at that. Let's take a break right now. That's a good point. 7 minutes, and then we'll cover some more. Okay, let's get started. So now we've covered a lot of ideas on heterogeneous multicore. One of the issues that exists in heterogeneous multicore is, as I said, if you ship some code to a particular server, you keep the shared data unlocks in that server, but now you need to send the private data, input data, to that server. The problem is you reduce the private data locality. And this happens actually in many execution models, not just heterogeneous multicore. Heterogeneous multicore is just one example. But I'll broaden the execution model a little bit. So staged execution model is a very general model. It's a general way of thinking about parallelism, actually. The goal is to speed up a program by dividing it up into pieces. It could be any kind of code piece, right? So you could consider threads as part of the staged execution model. You split the program code into segments. You run each segment on the core that's best suited to run it. That's the ultimate form of heterogeneity. And each core is assigned a work queue storing segments to be run. There are many benefits of this. Clearly, you get inter-segment parallelism. You can accelerate segments and critical paths using specialized or heterogeneous cores. And you improve locality of within segment data. So these are 3 key benefits that we've seen. So we're generalizing the model, actually. You could do this on any arbitrary thread execution. It's not just critical sections, right? You have just these notion of segments, and you specialize your execution units to those segments. In a sense, it's the ultimate form of heterogeneity. And if you can find common segments in code, you could have many of these specialized units, right? Okay. And simpler examples than what I just said is accelerated critical sections, bottleneck identification and scheduling, producer-consumer pipeline parallelism, and all of the task parallel models. If you have not read the Silk paper, I would definitely recommend that you read it. It's one of the earliest papers on task parallelism. But a lot of thread-based models, Intel thread and building blocks, and Apple's, I don't know what they call it right now, but at the time this presentation was prepared, it was called Grand Central Dispatch. They're all task parallel models. And, of course, special purpose cores and functional units fit into this as well. So at the very abstract level, you have this piece of code. You divide into segments. And instances of different segments go to different cores. And cores have work queues. These may be hardware work queues or software work queues. We're not going to go into that and deal with that. But this is very fine-grained parallelism now. These segments can be, I don't know, 5 instructions maybe. It doesn't have to be. It could be a million instructions also. They're basically grouped based on some property, which the programmer deemed or the compiler deemed important to group them in. So basically, you run one segment in one core, you spawn the other segment. That's one way. Maybe you can spawn many other segments also. And that segment spawns another segment. Accelerated critical section is an example. Basically, you have segment 0. That's the non-critical section. And you have segment 1. That's the critical section. Essentially, you divide your program into 2 segments, right? And the benefit is you get faster execution of a critical section, reduce serialization, improved shared data, and lock locality. Producer-consumer pipeline parallelism. You split a loop iteration into multiple pipeline stages, where one stage consumes data from the previous stage. One stage consumes data produced by... Why does it say the next stage here? That doesn't sound right? You consume data that's produced by the previous stage. Okay, that's a better idea. That's good. It's amazing that this slide survived years. So buggy programs exist, they survive decades also. This is less than a decade, but... Okay, basically in this case, the segment n is equivalent to stage n, right? Okay, and each stage runs on a different core. And the benefit is clearly stage-level parallelism, better locality. So programmer, hopefully, or somebody partitions the code such that you get very good locality within a stage, right? Or within instances of a stage that happen to be executed on the same core. But across the stages, you may actually be touching very different sets of data. That's one reason why you may want to partition things this way, right? And then you need to communicate some amount of data between the producer stage and the consumer stage. And of course, you could make this much more complicated. You could have multiple producers, multiple consumers, ... right? Okay, so the problem in any of these models actually try to keep the shared data in the same core. So stage 0, different instances get executed on the same core, and they hopefully share some data. That's one of the ways of dividing a loop iteration into multiple stages. The part of a loop that's operating on the same shared data is stage 0. It stays in core 0. The part of a loop that operates on another working set is divided into stage 1. It stays in core 1, ... So shared data locality, people are trying to optimize for. The problem is the trade-off. Now you put these stages into different cores. You reduce the inter-segment data locality or private data locality. For example, this core gets a cache miss on this load Y because that is produced by the previous segment running on some other core. So you need to somehow transfer it. You could rely on the cache coherence protocol, so you could wait. You could get here. When you get the cache miss, you ask, you do a broadcast on the Snoopy bus that we've talked about yesterday, and hopefully this core provides the data, right? But it takes time, and it stalls the execution. Same as here, this load Z needs to wait for the store Z to be transferred, the data to be transferred. So we've already seen this, right? Critical section incurs a cache miss when it touches data produced in the non-critical section. In other words, thread private data, right? So that's an example of inter-segment data. In producer-consumer pipeline parallelism, a stage incurs a cache miss when it touches data produced by the previous stage. This is correct now. That's interesting. Yeah. Basically, the performance of stage execution is limited by inter-segment cache misses. And there's some analysis in the paper that shows this. This is not the best analysis. We could have done a much better analysis, I think, because 10% doesn't sound that exciting, right? But this is basically, if you ideally get rid of this inter-segment transfers. So, for example, when a stage is, when in the critical section, you don't incur any cache misses due to private data, you get significant performance improvement. You get even more significant as the number of cores increases. So take this with a grain of salt. This is actually, in my opinion, one of the scalability problems with these stage execution or thread models in general. Pipeline parallelism, actually, you get higher performance improvement if you magically got rid of the L1 cache, the cache misses that you have due to accesses to inter-segment data. By the way, this is one of the beauties of simulation. You can simulate ideal mechanisms, right? High-level simulation. You can make your cache perfect, for example. The cache that you're implementing in your current lab, you could easily make it perfect in a timing simulator. You could always return a hit because you're not really executing the program for good. Right? And then you can figure out if my cache were perfect, if it always returned a hit when I asked for data, what would be my performance? Right? Okay, so let me give some terminology. How are we going to solve this problem? There are multiple solutions. I'll give you one hardware-software cooperative solution, but maybe there are purely hardware solutions as well to this. So inter-segment data is data. It's a cache block that's written by one segment and consumed by the next segment. Okay, so this is inter-segment data, basically. And that's transferred in cache blocks, Y and Z. Generator instruction is the last instruction to write to an inter-segment cache block in a segment. So the store Y is generating this inter-segment data. Store Z is generating this inter-segment data. So if we can somehow find these generator instructions and mark them, maybe we can do a much better job. So one of the observations is that it turns out the set of generator instructions is stable over execution time and across input sets. And the idea is to identify these generator instructions, record the cache blocks produced by those generator instructions, and proactively send those cache blocks to the next segment's core before starting the next segment. So basically, we want to be proactive about it. That's the idea. If you think about prefetching, for example, which we haven't talked about a lot, but you try to prefetch data. This is prefetching, except you're sending it to some other core. You're not prefetching to this core, right? You know, hopefully, what to send. Okay, so this is hardware-software cooperative. You may think about purely hardware solutions, which may be interesting also. But in this, let's discuss the hardware-software cooperative solution, because that may ease the hardware tasks a little bit. Basically, the compiler identifies generator instructions and inserts some instructions called marshalling. Right? So we use the terminology from remote function calls, actually. When you do a remote function call in a distributed system, you package your arguments and marshal them to a destination, to a server, basically. Essentially, this idea is very similar in that sense, except it's done in hardware. You want to do a remote function call to some other core, you marshal the arguments, except you don't know in this case, the goal is for performance. You want to proactively send those arguments. Okay, let's take a look at how we can do that. Basically, you need a profiling algorithm. You can also do code analysis, but profiling makes sense because there might be multiple paths actually that produce this load. Basically, intersegment data is produced by the store instruction. That's the last writer. And there may be other instructions inside that I don't show over here. You mark that last writer as the generator instruction, right? And there may be multiple generator instructions here, right? And then you need to somehow, assuming you mark the generator instructions now, you need to decide when to send the data and where to send the data. So that is communicated using some new instructions called marshal instructions. Marshal C1 means marshal all the data just generated by the generator instructions so far to core 1. And that core 1 can be a virtual ID that gets dynamically bound to a physical ID after things get scheduled. So there needs to be some runtime system that maps that, but let's not go into that right now. Okay, basically you insert the marshal instruction. Where do you insert the marshal instructions? One simple way is at the end of the segment, but you could actually insert it much earlier, right? Okay, so that's the compiler modification. So the profiler and the compiler marks these generator instructions, insert these marshal instructions. ISA needs to provide the generator prefix for stores, and it needs to provide the marshal instructions, and there needs to be some library or hardware mechanisms that binds the, not necessarily next segment ID, but this ID over here, virtual core ID, to a physical core ID, such that you know where to send this data that you've collected using the marshal instructions. And the hardware needs to have a buffer that keeps track of the physical address of cache blocks that need to be marshaled to some other core. And you can see the paper for analysis of this. It turns out this is not a lot of data, actually, but it's only your critical path. And it needs to have the ability to execute these new instructions. And it also needs to have this ability to push data to another cache, which is really interesting. It doesn't exist today. You can pull data from other caches, but you cannot push data to some other core's cache. It changes some things. But it's not hard to add, of course. If you're an architect, it's not. You need to be able to add this into the system. Okay. So let's look at the advantages and disadvantages. After that, I'm going to go into a little bit more detail. So this enables timely data transfer because you're trying to push the data to the core before the data is needed by the core. You want to prevent the core to stall, from stalling, right? You can marshal any arbitrary sequence of lines because you identify generator instructions, not patterns, right? You're not trying to identify, oh, I'm accessing this address A, P, C, D, and its pattern. You're not trying to identify that. You're really executing the instruction that's generating the data, hopefully. And you get low hardware cost because the hardware doesn't need to find these instructions. Okay. But of course, it may not be perfect because the profiler may mark something as a generator, and that generator executes, but then there might be an if later that executes another generator instruction, and that also generates another data, right? So you may actually marshal earlier or marshal unnecessarily, but it turns out that it doesn't happen very often. So the disadvantages is, of course, this requires profiler and ISA support. It's not always accurate. Well, I guess I already said this. You basically marshal more than needed. For example, you may marshal some data that's really not going to be used because the next segment may take another path of execution dynamically, right? Because you actually mark these generated sets based on some profiling. If your runtime set, data set is different from your profiling set, the path you take at runtime is different, you may actually marshal some data that's not needed to be marshaled. And this causes some waste. And it turns out this is not a big problem in the workloads that are examined because the number of inter-segment blocks is actually small, as I said earlier. But these are on the critical path, because once the segment, assuming the segment is on the critical path, once it gets to this instruction that's loading this data, it stalls, right? Because it's somewhere else. Okay, let's take a look at this example with critical sections. So we mark a generator instruction. That's the instruction that's basically stored, the push that I showed you earlier. It's really pushing some data into a location such that the critical section can actually pull from there. And this is, we're going to use the critical section call as a marshal instruction. So you could actually use the critical section call to trigger marshalling. So we're going to add this marshal buffer into every small core. And let's say small core is executing the non-critical section. It gets to the store Y. It stores the address of store Y into the marshal buffer. Later, it gets to the critical section call. And one of the things the critical section call does is it goes through the marshal buffer, takes the address in the marshal buffer, accesses the cache, and pushes the data and the address into the L2 cache and maybe the L1 cache of this large core. And the hope is that once this core starts executing, when it gets to the instruction that requires the inter-segment data, it gets a cache hit, as opposed to a cache miss. Right? Of course, this doesn't always work beautifully like this, because the distance matters when you marshal the data and when you need it over here. So marshalling as early as possible might be a good idea. Okay. So let's take a look at the performance of this. Again, the similar methodology as X-rated critical sections. And there are also prefetchers added so that to show that it's not a prefetching. These things are actually not easily prefetchable. We can talk about that when we talk about prefetching sometime. Okay, basically the performance improvement is on a 32-core equivalent system is about 9%. But it's almost equal to the ideal. Ideal meaning you get cache hits on all of these data, all of these inter-segment data, thread private data. And the performance improvement increases as the number of cores increases. And it turns out, as you can see, there are some workloads where private data locality is a problem, significant problem. So with some workloads, you get about 70%. So let's take a look at the same example with pipeline parallelism. Not even any specialization in that case. No large cores here. So the idea is more general, as I said earlier, right? Because it's really about private data locality. You add marshal buffers into the caches. Segment 0 gets executed. When it gets to the generator instruction, it inserts the address over here. If it gets to another generator instruction, it inserts another address over here. And when it gets to the marshal instruction, it basically, the control logic goes through the addresses over here, accesses the L2 cache, creates a packet with the address and the data, sends it to the core indicated by the marshal instruction. In this case, core that's executing segment 1. And when hopefully this segment executes the instruction that needs that data, it gets a cache hit. Right? That's the hope. So any kind of parallel program can actually take advantage of this, as you can see. Okay, so these are some workloads with pipeline parallelism, and it improves performance on those workloads also. It gets close to the ideal. So in some cases, of course, it turns out in some cases, the data that you need to marshal is a lot. As a result, you need a large marshal buffer. If your large marshal buffer is not large enough, you don't gain the ideal performance. You don't get close to the ideal performance. So there's analysis in the paper that shows that you get actually high coverage of these misses. Coverage of the misses means what fraction of these inter-segment misses can you actually capture. In critical sections, it's about almost 100%, meaning that you can, with this mechanism, 100% of the thread private data that you can cover and send to the large core, which is good, right? So these actually, if I take a step back, this thread private data is actually relatively easy to identify. So the designs that keep shared data local and ship the private data are easier designs than designs that actually move the shared data all around. So if you have a parallel system where you keep the private data in your own cache, but keep moving the shared data, people actually have put a lot of effort into predicting which core the shared data should go to. So that's a different approach, right? You start with a system where private data isn't local in each processor's cache, but shared data moves around. That's the regular multi-core systems that we have today. And many, many people across 30 years or 40 years right now have put effort into predicting which other core is going to touch this shared data and proactively sending that data to that core. And it turns out this is very difficult to do because you don't know really which other core is going to touch the shared data unless you schedule the threads in a manner that you know beforehand, which reduces your parallelism if you actually do that. Whereas this approach, keeping the shared data in your own local caches and predicting what private data you're going to send to someone else, is a lot easier because you actually can identify the private data much more easily, as we've just seen, right? You can look at these generator instructions, for example. Whereas shared data sharing, by definition, it's less deterministic because you don't know which thread is going to reach the critical section at what point in time, right? So these are two fundamental approaches to parallelism. And I think this approach is not surprising because shared private data is much more easily identifiable than shared data. Now, you can identify shared data, but you cannot identify who's going to touch it next. Okay, and this is timely. Basically, there's for some metric of timeliness that you should read the paper, you're timely, meaning whenever you ask for the data, it's actually in the cache with 80% probability. Accuracy is low, as you can see, because this is profiling based. Sometimes you identify these generated instructions. They're generated instructions, the profiling run, but when you actually run them, they're not generated instructions because the program in the next segment takes some other path. That's why the accuracy is low, which means that you marshal some data that's not going to be used. You waste some bandwidth and you waste some energy. But the medium accuracy doesn't impact performance a whole lot because there are a very small number of cache blocks that are marshaled for average segment. Okay, so why is this more interesting than it looks? Because the performance improvement actually increases as you add more cores, as you add higher interconnect latency, and as you make the caches larger and larger. Because inter-segment data misses become a bigger bottleneck. So as you parallelize more, and as you make things more scalable, this problem becomes worse. Because more cores add more communication. As a result, you get more of these inter-segment data communication. If you have higher latency in the interconnect, you get longer stalls due to communication, so pushing the data early, proactively, makes a bigger difference. And if you have a larger L2 cache, it doesn't matter for these misses. Because these are really communication misses, right? You're really communicating a piece of data that's produced here to somewhere else. And there's really no locality here unless you have a complete shared cache, of course, right? Between these. So larger L2 cache that's not shared doesn't help because these communication misses between private caches actually remain. Okay, there are many other applications of this which I'm not going to go into. Certainly task parallelism. You could do this to remote functional units. Computation. These are some approaches that you don't need to necessarily know about. But this one is actually interesting. This thread motion migration, this work actually said there are some cores that are tied to be different voltage and frequency. And instead of changing the voltage and frequency of different cores, we're going to make cores that are heterogeneous in terms of their voltage and frequency statically. And we're going to migrate threads to different cores. So if a thread needs more performance, it goes to a core that has higher voltage or higher frequency. It's an interesting approach, basically thinking about the problem in a different way. And that has some benefits also. So I think this actually can be an enabler for a more aggressive stage execution model because you lower the cost of data migration. And whenever you have remote execution of code segments, this overhead becomes very important. And if you want to become finer and finer grained in terms of tasks, like 2 instructions, if you want to ship 1 instruction, that's the ultimate form of parallelism, right? If you want to parallelize, that remote execution of finer grained tasks become more feasible. Okay. I think I already summarized this. Basically, you can potentially enable very fine-grained remote execution if you tackle this sort of locality. But what I said earlier actually is very interesting, and there needs to be more research done in this area, I think. Today, we're actually, a lot of the scalability bottlenecks are really caused by that cache coherence problem, right? If you actually move to a system like this, maybe you could also eliminate cache coherence. This is still not eliminating cache coherence. This is actually relying on cache coherence. But maybe there's a step on top of this. You have this execution model, that's stage execution, and you're shipping code to different places, and you're actually proactively pushing data. Do you really need cache coherence after that point? I don't know. Remains to be seen. Okay. In the remaining minutes, let me talk about a couple of other uses of asymmetry. Any questions so far? Is this interesting? Hopefully it's challenging some of your worldview a little bit also. I think in the end, this, at some point, maybe we will need to move away from thread-based programming models also. And this is, if you think about it, I said nothing about threads except for threading building blocks from Intel over here. These are really segments, right? It's really arbitrary execution segments. Okay, let's talk about other use of asymmetry. There are many other uses of asymmetry, as we've discussed, but I'd like to talk about the heterogeneous multi-core use. This is one of the earlier papers. The goal of this work was to improve energy efficiency, basically. The idea is to implement multiple types of cores on a chip, monitor the characteristics of this is for a single thread, or multi-programmed workloads. Whatever we discussed so far is for multi-threaded workloads. If you can monitor the characteristics of the running threads, you can dynamically pick the core that provides the best energy performance trade-off for a given phase, assuming you have different phases in a program. And best core depends on the optimization metric. For example, you want to optimize energy per performance, or performance per watt. Okay, so this is an example from that paper, actually. Basically, this shows, let's assume you have these 4 different cores that you've designed. And if you're a company like Alpha, or Digital Equipment Corporation, or Compaq, and if you don't exist anymore, you may still have these cores. Basically, you may already have these cores. That's the point. You may have a huge, beefy core, and you may have a very, very simple core. This is alpha 21 to 64, for example. All of these are scaled to 10 micron. And let's assume that you put them together. Now you can use them for optimizing energy efficiency, right? And this is the different power, average power, and IPC. So this EV8 has 2x IPC compared to EV4, but it has, I don't know, a lot more power. And if you execute a program segment, a program, on these cores, this is the power, this is the performance profile you get. EV8 is good, but not always really good. There are some cases where the performance of these cores is very close to each other, right? And this is the and you can also have a energy profile also. So collect some information while you're running, figure out when to switch to a core, and move the program to that core to maximize energy efficiency. If you want to know more, you should read the paper. But this basically enables, if you look over here, if you're optimizing for energy, for example, sometimes you run on EV8, sometimes you run on EV6, and a few points you run on EV4. If you're optimizing for energy delay, you never run on EV8. I don't know why. You can read the paper. And then you run on EV4 a lot of the time, right? So these are some examples, basically. You can the idea is core switching. Okay, so advantages, clearly you get more flexibility in energy performance trade-off. Again, heterogeneity enables more flexibility. You can execute computation to the core that's best suited for it. How do you design the cores? Again, it's similar. Yeah, so this actually has similar issues that, as we've discussed, incorrect predictions. Actually, the movement of an entire thread leads to potentially a lot of incorrect predictions. As a result, you may get the wrong core, reduce performance, or increase energy. So later, people have built on figuring out models as to when you should move from one core to another core in terms of both performance and energy. And overhead of core switching, clearly, and you clearly get the disadvantage of asymmetric CMP. And in this case, you also need phase monitoring and matching algorithms, right? What phase is good for what core? But this is true whenever you want to switch between cores, actually. It's a little bit different in the previous works we discussed, because we don't there you don't need to monitor the phase, right? You get program information, and the program tells you, oh, it may be a good idea to move over there, and you don't move everything, you move a small portion. Okay, what characteristics should be monitored? Once characteristics are known, how do you pick the core? So ARM's big and little actually has similar optimizations in its system to move between different cores. Okay, I think this is the last slide I will probably cover, unless the next one is really good. So advantage of asymmetric. Clearly, you can provide better performance when thread parallelism is limited. It can be more energy efficient. You can schedule computation to the core type that can best execute it. But, of course, there's always disadvantages with asymmetric also. You need to design more than one type of core. Is it true always? I asked this question. Maybe you design one type of core and you can morph that core. Scheduling always becomes more complicated. This is true for all of the previous works in bottleneck exploration. This is true for the energy optimization work. What computation should be scheduled on the large core? Who should decide? Managing locality and load balancing can become difficult if threads move between the cores. That's true for both the software as well as the hardware, as we've seen, right? Shared data locality versus private data locality. And cores have different demands from shared resources. So how do you handle the shared resources? We have not talked about this also. Okay, maybe I'll cover this slide too. We have time. So this is actually, we've covered, right, briefly. There are two different types. Type and power of cores can be fixed at design time. And basically, static asymmetry, you can have high-frequency cores, high-voltage cores, or build a more complex, powerful core with entirely different microarchitecture. Or you can have dynamic asymmetry. Type and power of cores change dynamically. And I've already posed this question. Is static asymmetry natural because there are chip-wide variations in frequency? There are two approaches to dynamically create faster cores. You can boost the frequency, which we have not talked about, actually. Under a limited power budget, you can actually boost frequency. Actually, existing processors do that. I think the name escapes me. Turbo Boost, right? Intel's Turbo Boost. I don't know if they renamed it recently again. They like renaming things. But Turbo Boost technology is essentially this. You can boost the frequency of one core and reduce the frequency of all of the other cores. Or you can combine small cores to enable a more powerful, complex core. Or you can reduce a bigger core into smaller cores. This is where we should stop. Well, maybe there are third, fourth, or fifth approaches also here. But I'll let you think about it if you're really interested in this one. There's actually more on this, but we don't have time. Any burning questions? Okay. Have a good weekend. I'll see you next week.